Look up at the night sky, at that vast ocean of darkness punctuated by countless points of light. It feels ancient, eternal, and overwhelmingly immense, doesn't it? We see stars being born and dying. We chart the orbits of distant galaxies. But what if I told you that the most profound story of our universe isn't written in the stars you can see, but in a faint, almost imperceptible glow that fills the entire cosmos? This is the cosmic microwave background, the oldest light in existence. It's the lingering echo of the universe's very first moment, the afterglow of the Big Bang itself, and it has been traveling across space for over 13 billion years to reach us. This primordial whisper holds within it the answers to our most fundamental questions, but it also presents us with a series of deep, confounding mysteries that defy our current grasp of physics. What if this ancient light doesn't just confirm our theories, but actively challenges them, pointing toward truths about reality that we have not yet even begun to imagine? This journey we're about to take together isn't just about distant cosmic phenomena. It's a journey to the very foundation of everything that is. The cosmic microwave background is our most direct window back to the infancy of the universe, a baby picture of reality when it was just a hot, dense soup of particles and energy. For decades, we've studied this cosmic fossil, mapping its subtle temperature variations with incredible precision, believing it would neatly confirm our understanding. But the more we look, the more we realize that this picture is far from complete. The CMB is not a simple, settled relic. It is a dynamic, puzzling tapestry woven with anomalies and inconsistencies that whisper of something missing from our cosmic model. We thought we were reading a straightforward history book, but instead we've found a gripping mystery novel full of clues that lead to more questions than answers. So today, we are going to explore 25 of the most astonishing and perplexing mysteries hidden within this ancient light. We will confront findings that suggest our universe might be lopsided, that hint at the presence of other universes beyond our own, and that challenge the very nature of space and time. We are going to peel back the layers of this cosmic onion, revealing secrets that could reshape our understanding of reality. This is a story of human curiosity reaching its absolute limits, of our relentless drive to understand our place in the cosmos. Get ready to have everything you thought you knew about the universe turned on its head, because the story written in this oldest light is stranger and more wonderful than anyone could have ever predicted. To truly appreciate the first great mystery, we need to step back in time, not just a little, but to a point just 380,000 years after the universe began. Before this moment, the cosmos was an opaque, searing fog of plasma, so dense that light couldn't travel freely. Then, in an event cosmologists call recombination, the expanding universe cooled just enough for atoms to form, allowing light to finally break free and race across the cosmos. That first flash of liberated light is what we now detect as the cosmic microwave background. But here is where the mystery begins. When we point our most sensitive telescopes in every conceivable direction, we find that the temperature of this ancient light is almost perfectly uniform. It's the same to an astonishing precision, a steady 2.7 degrees above absolute zero everywhere we look. Now, that might sound like a sign of a calm, orderly beginning, but for physicists it's deeply troubling. It's a problem of causality, a fundamental rule that says information cannot travel faster than the speed of light. Think of it like this. Imagine you walk into a massive, crowded auditorium and see that every single person from the front row to the very back is holding a cup of coffee at the exact same temperature. Not just similar, but identical down to a microscopic fraction of a degree. Your first question would be, how did they all coordinate this? Did they all get their coffee from the same central pot? In our universe, the coffee is the temperature of the CMB, and the auditorium is the entire observable cosmos. The problem is, according to the standard Big Bang model without any additions, there hasn't been enough time since the beginning for light or heat to travel from one distant side of the universe to the other to even out the temperature. These regions are separated by distances so vast that they were never in causal contact. They were beyond each other's particle horizons. It's as if people on opposite sides of the auditorium, who have never met or communicated, somehow managed to synchronize their coffee temperatures perfectly. This is the horizon problem. The universe appears to have coordinated itself on a scale that should have been impossible, leaving us with a fundamental question. How did these disconnected regions all agree on the same conditions? This profound puzzle led to one of the most influential ideas in modern cosmology, cosmic inflation. The theory proposes that in the very first fraction of a second after the Big Bang, the universe underwent a period of exponentially rapid expansion, ballooning from a subatomic speck to a much larger size in an unimaginably short time. This violent stretching would have taken a tiny, causally connected patch of the early universe and blown it up to become our entire observable cosmos, effectively ironing out any temperature differences and giving us the uniformity we see today. Inflation is an elegant solution, and it has become a cornerstone of our cosmic model. But is it the final answer? While inflation explains the uniformity, it also introduces new layers of mystery. We don't know what drove this inflationary expansion, what stopped it, or if it was a single event. Some physicists wonder if inflation is a necessary truth, or if it's a clever patch that covers a deeper ignorance. The horizon problem, therefore, remains a gateway mystery. It forced us to invent a radical new concept to solve it, but in doing so, it opened a door to even grander questions about the true nature of the universe's first moments. But that initial moment of perfect uniformity leads us directly to another profound mystery, one that involves a type of particle that should be everywhere but is strangely, completely absent. This is the mystery of the missing magnetic monopoles. You are familiar with magnets. Every magnet you've ever held has a north pole and a south pole. If you break a bar magnet in half, you don't get an isolated north and an isolated south. You get two smaller magnets, each with its own pair of poles. This is a fundamental feature of classical electromagnetism. However, many of our most ambitious theories that attempt to unify the fundamental forces of nature, theories known as grand unified theories, strongly predict the existence of a magnetic monopole. This would be a particle that is, in essence, a solitary north or south pole, a fundamental and isolated source of magnetic charge. According to these theories, the conditions in the incredibly hot, dense early universe were just right for these exotic particles to be forged in staggering numbers. The physics suggests that monopoles would have been produced as stable, heavy relics, essentially fossils from when the electromagnetic, weak, and strong nuclear forces were all one unified force. The problem is, if these theories are correct, the universe should be absolutely flooded with magnetic monopoles today. Their predicted density is so overwhelming that they would be a dominant component of the mass in the universe. They would affect the formation of galaxies, the dynamics of cosmic structures, and their collective influence would be clearly written into the patterns of the cosmic microwave background. We would see their imprint everywhere, and yet, after decades of dedicated searching with increasingly sensitive experiments, we have not found a single confirmed magnetic monopole. It's as if a fundamental law of a unified universe left a signature that we know must be there, but when we look for it, the page is completely blank. Once again, the theory of cosmic inflation provides a potential escape route. The same period of hyper-expansion that solved the horizon problem would also have dramatically diluted the density of any primordial monopoles. Imagine a drop of ink in a vast ocean. That's what inflation would have done to these particles, spreading them so thin across the cosmos that the chance of one ever passing through our detectors becomes infinitesimally small. On the surface, this is another brilliant success for the inflationary model. It elegantly explains two major puzzles with one single mechanism. but this solution forces us to confront a deeper, more philosophical question. Is inflation truly solving the monopole problem, or is it simply making the evidence for it disappear? We are in the curious position of having a theory that predicts a phenomenon, and then invoking another theory to explain why we cannot observe that very phenomenon. It's a bit like a detective who explains the lack of fingerprints at a crime scene by proposing a windstorm that blew all the evidence away. It's a perfectly plausible explanation, but it also makes it impossible to verify whether the fingerprints were ever there in the first place. This leaves us wondering if we've uncovered a profound truth about the universe's infancy, or if we have merely found a mathematically clever way to hide a deep inconsistency in our theories. Moving from the puzzle of missing monopoles, we encounter a third and perhaps even more profound question about the very shape of our cosmic home. This is known as the flatness problem, and it deals with a staggering level of fine-tuning in the universe's initial density that seems to defy mere chance. To understand this, we need to introduce a crucial number that cosmologists call omega. Omega represents the ratio of the actual density of matter and energy in the universe to the critical density, the precise amount needed to just barely halt the universe's eternal expansion. If omega were less than 1, the gravitational pull of all the cosmic material would be too weak to overcome the momentum of the Big Bang, and the universe would expand forever, ultimately becoming a cold, dark, and infinitely vast emptiness. If omega were greater than 1, gravity would eventually win, pulling all matter and energy back together in a spectacular reversal of the Big Bang known as the Big Crunch. But our most precise measurements, especially from the cosmic microwave background, tell us that omega is not just close to 1, it is almost exactly 1. A value of exactly 1 signifies a flat universe, one that will continue to expand forever, but at a rate that slows towards 0, perfectly balanced on the knife's edge between these two dramatic fates. The sheer perfection of this balance is what makes it so mysterious. Think of it like trying to balance a pencil perfectly on its sharpened tip. In your hand, it will always fall over. But if you could somehow balance it with an accuracy of 1 part in a million billion, it might stand for a few moments. Now, imagine the universe as that pencil. For it to have survived for over 13 billion years without either collapsing back on itself or flying apart into utter nothingness, the initial conditions at the moment of the Big Bang had to be fine-tuned to an almost incomprehensible precision. The density of the early universe had to be set to a value of 1 with a margin of error of just 1 part in 10 to the power of 60. That number is so vast it's difficult to even visualize. It is a 1 followed by 60 zeros. To put that in perspective, the number of atoms in the entire observable universe is estimated to be around 10 to the power of 80. This level of fine-tuning is equivalent to throwing a dart from one side of the observable universe and hitting a bull's-eye just 1 millimeter wide on the other side. It seems statistically impossible, a setup so perfect that it feels less like a random occurrence and more like the universe was deliberately designed to be this way. This unnatural fine-tuning is another problem that the theory of cosmic inflation elegantly resolves. The incredibly rapid expansion in the universe's first moments would have acted like a cosmic iron, relentlessly smoothing out any curvature. No matter what the initial geometry of the universe was, whether it was positively curved like a sphere or negatively curved like a saddle, this violent stretching would have driven it toward perfect flatness. Imagine drawing a small, intricate curve on the surface of a balloon. As you inflate the balloon to an enormous size, that tiny section of the surface you marked becomes larger and larger, and the curve you drew appears to become flatter and flatter from your local perspective. Inflation does this to the entire fabric of spacetime, dynamically forcing omega toward the value of 1 we observe today. So, once again, inflation provides a compelling mechanical answer, transforming a seemingly miraculous initial condition into a natural consequence of a physical process. Yet this solution also deepens the mystery. We are left to wonder, is cosmic inflation the fundamental engine that shaped our reality, or is it a convenient mathematical framework that explains away several profound coincidences? The perfect flatness of our universe, as captured in the ancient light of the CMB, remains one of the most powerful clues that our standard story of the cosmos is missing a crucial foundational chapter. But just as inflation seems to provide such elegant solutions, we are confronted with a finding so strange and so unsettling that it has earned a dramatic nickname among cosmologists, the axis of evil. This mystery strikes at the very heart of a principle that has guided our understanding of the cosmos for over a century, the cosmological principle. This foundational idea states that the universe is, on the largest scales, both homogeneous and isotropic. Homogeneous means the universe has a uniform distribution of matter, while isotropic means it looks the same in every direction. There are no special places and, crucially, no special directions. The universe, in essence, should have no center and no edge. It should be a vast, featureless expanse where the laws of physics are the same everywhere. The cosmic microwave background, in its near-perfect uniformity, has long been considered the ultimate proof of this principle, but the axis of evil suggests there might be a crack in this foundational pillar. To grasp what this axis is, we need to understand how scientists read the CMB. They don't just look at a simple picture, they perform a complex mathematical breakdown called a multipole expansion. Think of it like listening to a symphony. The overall uniform temperature of the CMB is like the steady, constant hum of the orchestra's tuning note. That's the monopole. The next layer of detail, the dipole, is like the music's overall volume shifting because we are moving through space, similar to how the pitch of a siren changes as an ambulance passes you. But beyond that, we get into the harmonics and melodies, the quadrupole and octupole. These are the subtle, large-scale patterns of slightly hotter and colder spots that tell us about the fundamental vibrations of the infant universe. According to the cosmological principle, these patterns should be randomly oriented with no correlation to any particular direction in the sky. They should be like splatters of paint on a canvas with no inherent alignment. The shocking discovery, however, was that these larger-scale patterns, the quadrupole and octupole, are not random at all. Their hot and cold spots appear to be aligned with each other along a specific preferred axis that runs through our solar system. Even more bizarrely, this same axis seems to be strangely aligned with the plane of our solar system and the direction of the sun's motion through the cosmos. It's as if the universe's oldest fossilized whisper is somehow aware of our local cosmic neighborhood, which, on the grand scale of things, should be completely insignificant. The name axis of evil was coined partly in jest, reflecting how this alignment is so philosophically troubling that it feels almost personally antagonistic to our fundamental models. If true, it suggests that we do live in a special place, looking out at a universe that has a fundamental architecture, a preferred direction woven into the fabric of space-time itself. Naturally, this has sparked intense debate. The primary question is whether this alignment is a real physical phenomenon or simply a statistical fluke, a cosmic mirage born from the limitations of how we observe the universe. Skeptics argue that when you have a vast amount of data, you're bound to find some seemingly strange correlations purely by chance. They point out that we have only one universe to observe and we can only see one CMB sky. This makes it incredibly difficult to perform a true statistical test, as we lack other universes for comparison. Some researchers have proposed that the effect could be caused by foreground contamination from our own galaxy, or even by the way we process the raw data to remove its influence, inadvertently imprinting a preferred direction on the result. Yet, despite years of scrutiny and more precise data from satellites like Planck, the anomaly has stubbornly refused to go away. It persists at a confidence level that makes it hard to dismiss entirely. If this axis is indeed a real feature of our cosmos, the implications are nothing short of revolutionary. It could mean that the universe is not isotropic, but has a large-scale rotational structure or a global anisotropy that influences the formation of everything within it. It might point toward exotic physics, such as the universe being a rotating cylinder or having a non-trivial topology, like being shaped like a giant donut. It could even be a hint that our universe is but one bubble in a vast multiverse, and the axis of evil is a scar from its violent birth, a bruise left from a collision with another universe in the cosmic foam. This single, spooky alignment in the oldest light we can see reminds us that for every answer we find, the universe is always ready to present us with a deeper, more confounding question. Just when we start to feel comfortable with the idea that the universe is fundamentally uniform, it presents us with a feature so bizarre and so out of place that it seems to defy all reasonable explanation. This is the mystery of the cold spot, a vast and profoundly cold region in the cosmic microwave background that stands out like a cosmic bruise on an otherwise smooth canvas. Discovered in the data from the Wilkinson Microwave Anisotropy Probe, or WMAP, and later confirmed with even greater precision by the Planck satellite, this anomaly is not just a minor statistical blip. It is a colossal region of space spanning nearly 1.8 billion light-years across, where the temperature of the ancient light is significantly colder than the surrounding average. The odds of such a feature appearing randomly in a universe that adheres perfectly to our standard model are astronomically low, estimated to be around 1 in 200. This isn't just a curiosity, it is a direct challenge, a persistent thorn in the side of cosmological orthodoxy that demands an answer. So, what could create such a gigantic cold patch in the universe's first light? Scientists have put forward two primary classes of explanation, one that works within the known laws of physics and another that ventures into the truly speculative realms of cosmology. The more conventional hypothesis proposes that the cold spot is not an intrinsic feature of the CMB itself, but rather an illusion caused by a vast, largely empty region of space lying between us and the surface of last scattering. This hypothetical structure is known as a supervoid. The mechanism at work here is called the integrated Sachs-Wolf effect. To understand this, imagine a photon of CMB light traveling toward us for billions of years. As it journeys through the cosmos, it passes in and out of regions of varying gravitational pull. When it enters a gravitational well like a cluster of galaxies, it gains energy, making it appear slightly hotter or blue-shifted. But when it climbs out, it loses that energy, appearing slightly colder or redshifted. In a universe that is not expanding at an accelerating rate, these effects would cancel each other out perfectly. However, because dark energy is causing the expansion of the universe to accelerate, the gravitational wells and hills are actually flattening out over time. This means a photon climbing out of a potential well loses more energy than it gained when it fell in. If a photon passes through a giant, deep void, a region of significantly below average density, it will effectively be climbing out of a gravitational hill for a very long time, losing a substantial amount of energy along the way. By the time it reaches our telescopes, it would appear noticeably colder. In this scenario, the cold spot is a shadow, a cosmic mirage cast by one of the largest structures we could possibly imagine. The search for this proposed supervoid, however, has been fraught with controversy and conflicting results. Astronomers have scanned the direction of the cold spot and have indeed found evidence of a large underdensity of galaxies, a void that seems to correlate with its position. But there's a major problem. The void they've found, while large, does not appear to be nearly vast or empty enough to account for the dramatic temperature drop we observe in the cold spot. The numbers simply don't add up. The observed underdensity would only cause a small fraction of the cooling we see. This leaves us with a troubling possibility. Either we have not yet fully mapped the true extent of this void, and it is far larger and emptier than our current surveys can detect, or the supervoid explanation is incomplete, and we are missing a crucial piece of the puzzle. This gap between prediction and observation keeps the mystery alive and forces us to consider far more exotic possibilities. This brings us to the second, and undoubtedly more spectacular, theory, that the cold spot is the imprint of a collision with another universe. This idea emerges from the framework of eternal inflation and the multiverse. In this model, our universe is just one expanding bubble in a frothing, infinite meta-universe, where new bubble universes are constantly budding off and inflating into existence. Sometimes these bubbles can collide. The theory suggests that if a neighboring universe had bumped into our own while it was still in its inflationary infancy, the energy released at the boundary of that collision would have left a distinct signature on our cosmic microwave background. The interaction would have effectively drained energy from the photons in that region, creating a vast circular area that is significantly colder than its surroundings. The cold spot in this breathtaking interpretation is a cosmic scar, a bruise left on our universe from a violent encounter with a separate reality in the greater multiverse. Of course, confirming such a profound idea is monumentally difficult. We cannot rewind the tape of cosmic history to witness the collision, and we certainly cannot travel beyond our own universe to find the culprit. The evidence must come from a detailed statistical analysis of the CMB itself, looking for specific patterns within the cold spot that match the predictions of a bubble collision model. So far, the data has been tantalizing but inconclusive. Some analyses claim the spot's profile is consistent with a collision, while others argue its properties are not unique enough to rule out a rare but natural fluctuation in the primordial density field. The cold spot, therefore, remains in a state of limbo. It is a celestial Rorschach test where cosmologists see either a fascinating cosmological structure that pushes the limits of known physics or a doorway to an entirely new multiverse paradigm. Its very existence is a humbling reminder that our map of the cosmos, drawn from the ancient light of the Big Bang, still contains unexplored territories marked quite literally, "Here be dragons." And just as the axis of evil suggests a preferred direction in the heavens, another profound anomaly hints that the universe might not be the same on all sides, presenting us with the mystery of the hemispherical power asymmetry. Think back to the idea of the CMB as a symphony of the early universe. The cosmological principle tells us that this cosmic music should sound the same no matter which way we face. The statistical properties of its hot and cold spots, its harmonies and its rhythms, should be identical in every hemisphere of the sky. But when scientists from the Planck mission and others before them performed a meticulous statistical analysis of the CMB's temperature fluctuations, they found something deeply unsettling. The universe appears to be playing its symphony slightly louder in one half of the sky than in the other. In one celestial hemisphere, the temperature variations are slightly stronger, showing more pronounced hot and cold spots, while the opposite hemisphere is comparatively muted with weaker fluctuations. This isn't about a single cold spot or a specific alignment, but a fundamental statistical imbalance across vast swaths of the cosmos. It's as if you were listening to a stereo recording where the left speaker consistently has more power and presence than the right, suggesting the recording studio itself was somehow lopsided. For cosmologists, this detection is not a minor curiosity. It is a direct challenge to the principle of statistical isotropy, which is a cornerstone of our entire cosmological framework. The universe, on its largest scales, is simply not supposed to have a preferred powerful side. The odds of such a pronounced hemispherical asymmetry arising by pure chance in a statistically isotropic universe are extremely low, again forcing us to question whether we are seeing a rare statistical fluke or a genuine crack in our foundational model. This finding is made even more intriguing by the fact that the axis that divides these two hemispheres of unequal power is very close to the one identified for the axis of evil. This convergence of independent anomalies along a similar direction makes it much harder to dismiss them as mere coincidences. It increasingly points toward a single underlying cause, a fundamental lopsidedness woven into the fabric of our observable universe. What could possibly cause such a large-scale power imbalance? One compelling line of thought points to the very beginning of everything, to the era of cosmic inflation. Some theoretical models suggest that this asymmetry could be the imprint of primordial gravitational waves, ripples in the fabric of spacetime itself, that were not uniform in all directions. If the field that drove inflation had a slight directional preference, it could have generated gravitational waves that were stronger in one plane, which in turn would have imprinted a power asymmetry on the CMB. Another, even more radical idea is that the universe is fundamentally anisotropic on its grandest scales. Perhaps the cosmos is not a perfectly symmetrical expansion from a point, but has a subtle, inherent directionality to its structure, like a crystal that has a grain. In this view, the laws of physics themselves might operate with a slight directional dependence over cosmological distances, a concept that would completely upend our current understanding. A different class of explanation looks not at the universe's fundamental nature, but at our movement through it. It is possible that this asymmetry is not intrinsic to the CMB, but is instead a Doppler-like effect caused by our solar system's high-speed motion relative to the CMB's rest frame. While we already account for the basic dipole caused by this motion, some physicists speculate that more complex relativistic effects, collectively known as the kinetic Doppler quadrupole, could subtly distort the statistics of the fluctuations, making one hemisphere appear more powerful than the other. Yet, detailed calculations have so far shown that this effect is too small to fully account for the observed asymmetry, leaving the mystery largely intact. Ultimately, the hemispherical power asymmetry forces us to confront a deeply philosophical question about our place in the cosmos. Are we, in fact, located in a slightly special part of a slightly lopsided universe? The principle that we do not occupy a privileged location has been a guiding light for centuries of scientific discovery, but these persistent asymmetries, all hinting at a preferred axis, suggest that on the very largest scales, the universe may have a grand architecture, a fundamental grain against which we are all aligned. It's a humbling thought that the oldest light in creation might be telling us that the cosmic stage is not perfectly symmetrical, and that we are seeing the performance from a seat that offers a distinctly unbalanced view. If the universe were truly a random, isotropic place, then its oldest light should show a certain level of structure at every conceivable scale, from the very small to the grandest imaginable. This expectation leads us directly to our seventh mystery, a subtle but profound statistical oddity known as the lack of large-angle correlations. To grasp what this means, picture the map of the cosmic microwave background with all its intricate hot and cold spots. Now, imagine choosing two random points on this celestial map that are separated by a very wide angle, say, more than 60 degrees apart on the sky, which is a truly vast distance. A correlation function is essentially a mathematical tool that asks a simple question. What is the likelihood that the temperature at one of these points is related to or correlated with the temperature at the other? In a universe that adheres perfectly to our standard model, we would expect to find a certain amount of this large-scale relationship. The primordial plasma of the early universe was sloshing with sound waves, and just as a large drum can produce deep, resonant low notes, the infant cosmos should have been filled with the longest wavelength vibrations, creating subtle temperature relationships across the biggest patches of the sky. The astonishing finding from missions like WMAP and Planck is that this expected relationship is missing. At the very largest angular scales, the temperature fluctuations in the CMB are significantly less correlated than our best theories predict. It's as if you are listening to a symphony and realize that the deepest, most resonant notes from the tubas and double basses are strangely muted or entirely absent. The music of creation is playing, but the bass line has gone quiet. The statistical significance of this deficit is hard to ignore. The probability that it's a simple fluke is less than 1 in 1,000. This isn't a dramatic visual feature like the cold spot, but a subtle statistical ghost in the machine, a ghost that nonetheless haunts the foundations of cosmology. This missing power on grand scales represents another crack, however fine, in the edifice of the cosmological principle. It suggests that the universe might be lacking structure on its very largest scales, that the mechanisms which seeded all cosmic structure somehow failed to operate across the most immense distances. One captivating explanation for this missing correlation ventures into the mind-bending possibility that our universe is not infinite, but finite and wrapped in on itself in a complex shape, a concept known as a non-trivial topology. In an infinite, flat universe, there is no limit to the size of the waves that can exist in the primordial plasma. But if the universe is finite, there is a fundamental cutoff. Think of it like the vibrations on a drumhead. A small, circular drum can only produce notes with wavelengths that fit neatly onto its surface. It cannot produce a sound wave that is larger than the drum itself. If our observable universe is but a small patch of a larger, finite cosmos with a complex topology, perhaps shaped like a giant donut or a twisted chamber, then the longest possible waves that could have existed in the early universe would have been limited by the overall size of this cosmic container. The lack of correlations at the largest angles we can observe would then be a direct consequence of this. We are simply not seeing waves that were too big to fit inside the universe at the time the CMB was formed. In this scenario, the muted bass notes in the cosmic symphony are silent because the cosmic drum simply wasn't big enough to produce them. A different, equally profound idea points to the very beginning of inflation. Perhaps the period of hyper-expansion did not start from a true singularity, but was preceded by a different phase of the universe, often called a pre-inflationary era. If this was the case, the rapid stretching of space-time might not have had enough time to fully amplify the very longest wavelength fluctuations. These grandest waves would have been born before inflation began, and the inflationary process, while tremendously effective at amplifying smaller waves, may have only partially stretched these primordial giants, leaving them with less power than we expect. It's as if the universe's amplifier was turned on a moment too late to fully boost the deepest sounds from the cosmic band. This idea suggests that the CMB might contain a fossilized imprint from the epoch before inflation, a time about which we currently have no direct evidence. The lack of large-angle correlations could therefore be a window into the conditions that existed before the inflationary Big Bang, a whisper from a time we thought was forever lost to physics. Yet another perspective considers whether we are being misled by a cosmic selection effect. We have only one universe to observe, and we are sitting in one specific location within it. It is statistically possible, though unlikely, that we just happen to be in a region where the largest scale fluctuations are unusually quiet. Perhaps in other parts of the cosmos, the correlations are stronger, but from our particular vantage point, the universe appears oddly smooth on the grandest scales. While this possibility can never be entirely ruled out, the persistent nature of this anomaly, coupled with others like the axis of evil, makes it increasingly difficult to dismiss as mere luck. The quiet vastness at the largest angles of our sky remains one of the most subtle and yet deeply significant puzzles in modern cosmology. It forces us to question the very geometry and history of our cosmic home, suggesting that either its shape is more complex than a simple infinite plane, or its first moments were far more intricate than the smooth, relentless expansion we have long imagined. But to truly grasp the strangeness of this cosmic axis, we need to look deeper into the specific mathematical layers of the CMB, at the patterns known as the quadrupole and the octupole. Think of the universe's background radiation not as a simple, smooth glow, but as a complex shape like a celestial balloon. The simplest, perfectly round balloon represents the uniform temperature, that's the monopole. The next layer of complexity is the dipole, which is like the balloon being slightly stretched in one direction because we're moving through space. But after that, we encounter the true fingerprints of the infant universe's fundamental vibrations, the quadrupole and the octupole. The quadrupole is the simplest deviation from a perfect sphere. If you could hold it in your hands, it would feel like a ball that's been gently squeezed at the poles and bulges at the equator, or perhaps pinched in one plane, creating a kind of cosmic peanut or dumbbell shape. It represents the most basic, large-scale hot and cold spots arranged in a two-lobed pattern. The octupole is the next level of complexity, a shape with 4 pairs of hot and cold spots, like a more intricate, lumpy potato. These aren't physical shapes in space, of course, but mathematical descriptions of the dominant temperature patterns on the largest scales. According to our fundamental principles, these two distinct patterns, the simple cosmic peanut and the more complex cosmic potato, should be oriented completely randomly with respect to each other. Their planes of symmetry should have no reason to align. It would be like tossing 2 separate handfuls of toothpicks onto a table. You'd expect them to land pointing in every which direction with no overall coordination. The shock came when cosmologists analyzed the real data. They found that the planes of these two fundamental shapes, the quadrupole and the octupole, are not randomly oriented. Their hot and cold spots are oddly coordinated, as if they were both influenced by the same underlying directional preference. Even more bizarrely, this shared alignment, or plane, is not just some arbitrary line through the cosmos. It appears to be curiously linked to our own local cosmic environment, roughly aligning with the plane of our solar system and the direction in which the sun is moving. This is what makes the anomaly so philosophically jarring. The largest scale patterns imprinted on the universe at its birth seem to be aware of our insignificant little planetary system, which, on the cosmic scale, should be a complete non-factor. It's as if the grand fresco painted on the ceiling of the Sistine Chapel had brushstrokes that subtly aligned with the specific floor tiles directly beneath your feet. The connection feels unnervingly personal and defies the Copernican idea that we do not occupy a special place. The statistical significance of this alignment is a subject of intense study and debate. Initial analyses suggested the odds of such a coordinated orientation happening by pure chance in an isotropic universe were less than 1 in 1,000. While later, more refined studies have sometimes found the significance to be slightly lower, the anomaly has proven to be stubbornly persistent. It refuses to be washed away by more precise data from the Planck satellite. This resilience is what forces scientists to take it seriously. It's not just a single weird data point. It's a consistent, strange signal that challenges our most basic assumptions. If this is not a fluke, the implications are profound. It suggests that the universe is fundamentally anisotropic on its largest scales. The Big Bang may not have been a perfectly symmetrical explosion in all directions, but rather an event with a slight directional preference, a kind of cosmic grain, woven into the fabric of spacetime from the very first instant. This primordial anisotropy could have acted as a guiding template, influencing the formation of all subsequent structure, from the vast cosmic web of galaxies down to the very orientation of our solar system. The alignment we see today would then be a fossilized echo of that initial lopsidedness. Several theories attempt to explain how such a fundamental anisotropy could arise. One possibility involves the inflattened field, the mysterious energy that drove cosmic inflation. Perhaps this field was not perfectly uniform, but had a slight directional dependence, a tilt, that caused the universe to stretch slightly more in one direction than in others. This would have imprinted a preferred axis onto the density fluctuations, which then showed up as the aligned quadrupole and octupole. Another, even more exotic idea is that the universe itself is rotating. A very slight overall rotation or vortex to the cosmos could have twisted these large-scale patterns into alignment. While the evidence for large-scale rotation is extremely weak, the idea highlights the kind of radical rethinking this anomaly demands. A third, deeply fascinating possibility is that this alignment is a signature of the universe's topology, its overall shape. If the universe is finite and has a complex shape like a twisted cylinder or a vast donut, the geometry of that shape would impose specific restrictions on the wavelengths of the vibrations it can support, potentially forcing the largest patterns to align in a particular way. In this view, the quadrupole and octupole alignment is a clue to the true and likely mind-bending geometry of our cosmic home. Ultimately, whether the cause is a tilted inflation, a cosmic spin, or a non-trivial topology, the coordinated dance of the quadrupole and octupole stands as one of the most direct and puzzling hints that our universe's birth was far more complex and textured than the perfectly smooth, symmetrical beginning we have long imagined. After exploring the universe's large-scale geometry and alignment, our investigation takes a more subtle turn, from the grand patterns of hot and cold spots to the very color and quality of the light itself. This brings us to the profound mystery of spectral distortion anomalies. Up to this point, we've been talking about the cosmic microwave background as a temperature map, but it's also a spectrum. Every object with a temperature emits a characteristic spread of radiation across different wavelengths, a pattern physicists call a blackbody spectrum. A perfectly heated object like the theoretical blackbody emits light with a specific, smooth, and predictable curve. When the universe became transparent during recombination, the light released was, for all intents and purposes, a nearly perfect blackbody, a snapshot of the universe at a single, searing temperature. But this incredible perfection is, in itself, a major puzzle. Think of it like the pure, steady tone from a perfectly tuned musical instrument. Now, imagine that throughout the history of the cosmos, numerous events should have acted like someone randomly plucking a guitar string or banging a drum in the middle of that sustained note. These events, things like the explosive energy of the first stars, the violent demise of early black holes, or the gradual decay of exotic dark matter particles, would have injected enormous amounts of energy into the cosmic plasma. This injected energy should have disturbed the pristine blackbody, causing what scientists call a spectral distortion. It would be like heating that perfectly tuned instrument. The quality of its sound would change slightly, developing a different timbre or a faint harmonic. These distortions are not about temperature differences from one point to another, but a change in the very character of the radiation across the entire sky. They are the subtle, cosmic equivalent of a fingerprint left at a crime scene, evidence of violent or energetic events that occurred long after the Big Bang's initial flash. The truly baffling part is what we found when we went looking for these fingerprints. In the 1990s, the COBE satellite's FERA's instrument measured the CMB spectrum with breathtaking precision. The result was astonishing. The cosmic microwave background is the most perfect blackbody ever measured in nature. The data points from the real universe fell exactly on the predicted theoretical curve, with any deviations being so minuscule they were lost in the instrument's noise. The CMB wasn't just a good blackbody, it was an impossibly perfect one. This phenomenal smoothness places incredibly tight limits on how much energy could have been dumped into the universe at various times in its history. It's as if we discovered a 380,000-year-old fossil that looks as pristine and undisturbed as the day it was formed, despite knowing that the world around it experienced earthquakes, floods, and volcanic eruptions for billions of years. The silence is deafening. Where is all the expected cosmic graffiti? This creates a significant tension between theory and observation. we have strong reasons to believe that a lot of messy astrophysical activity should have happened. For instance, the process of structure formation, where gravity pulled matter together to form the first stars and galaxies, is thought to have been incredibly violent. As vast clouds of gas collapsed, they would have generated shock waves and heated the surrounding intergalactic medium, pumping energy into the cosmos that should have left a measurable distortion. Another major candidate is decaying or annihilating dark matter. If the mysterious particles that make up dark matter are unstable and can decay into standard particles, or if they can collide and annihilate each other, these processes would release a flood of energy and radiation. This energy injection would have heated the cosmic plasma, creating a clear spectral signature that we should be able to detect. The fact that we see no such signature means that either dark matter is far more stable and less interactive than many popular theories suggest, or that these energy releases happened at a time or in a way that left no discernible mark on the CMB spectrum. What does this cosmic silence ultimately tell us? It acts as a powerful, if frustrating, constraint on the history of our universe. It tells us that the universe must have been surprisingly calm and orderly for long stretches of its adolescence. The era of reionization, when the first stars flooded the cosmos with ultraviolet light, must have been a relatively gentle and prolonged process rather than a sudden, cataclysmic energy dump. It suggests that the nature of dark matter is such that it does not readily dump energy into the primordial plasma, ruling out entire classes of theoretical models. The pristine nature of the CMB spectrum is like a strict cosmic editor, cutting out whole paragraphs of potential history that we thought were part of the story. It forces us to consider that the universe's journey from a hot, dense state to the structured cosmos we see today may have been a far more graceful and less tumultuous transition than we ever imagined. A quiet evolution whose deepest secrets remain locked within the perfect, unblemished curve of the universe's first light. Now our journey takes us from the grand geometry of the cosmos to the very building blocks of matter, connecting the ancient light of the CMB to the chemistry of the first stars. This is the enduring mystery of the lithium problem, a puzzle that pits our most precise measurements of the infant universe against the observed contents of some of its oldest stellar inhabitants. To understand this conflict, we need to travel back even further than the moment the CMB was released, to a time just minutes after the Big Bang, an epoch known as Big Bang nucleosynthesis or BBN. In this cosmic pressure cooker, the entire universe was a searing hot nuclear fusion reactor. Protons and neutrons zipped around at incredible speeds, colliding and sticking together to form the nuclei of the very first light elements. In a frantic few minutes before the expanding universe cooled and thinned out too much for nuclear reactions to continue, the primordial soup cooked up most of the universe's hydrogen, its heavier isotope deuterium, a substantial amount of helium, and a tiny, trace amount of the element lithium. The beautiful part of this story is that the precise conditions of this cosmic forge are not a mystery. We can use the cosmic microwave background as a cosmic thermometer and barometer. The exquisite details of the CMB's temperature fluctuations allow us to calculate the density of ordinary matter in the universe with incredible accuracy. And since BBN was entirely governed by the density of this ordinary matter and the expansion rate of the universe, we can plug these CMB-derived numbers into our theoretical models and generate firm, testable predictions for how much of each primordial element should have been created. For deuterium and helium-4, the agreement between the BBN predictions and the abundances we actually measure in ancient cosmic clouds and old stars is spectacularly good. It's a triumphant confirmation of the Big Bang model, but for one specific isotope, lithium-7, the cosmic math goes completely awry. The predicted abundance from BBN is about 3 times higher than what we consistently observe in the atmospheres of the most ancient stars in our galaxy. The universe's recipe, written in the CMB, calls for one amount of lithium, but the oldest stars in our cosmic neighborhood show a clear shortage. It's as if we followed a time-tested recipe for a cake perfectly, but when we taste it, one key ingredient is mysteriously missing. So, where did the lithium go, or was it never made in the expected quantities to begin with? Scientists have been grappling with this question for decades, and the proposed solutions span the entire spectrum from revisions to known nuclear physics to the invocation of entirely new particles. One line of investigation questions whether our understanding of the nuclear reaction rates themselves is complete. Perhaps there is an unaccounted-for nuclear reaction pathway in the BBN chain that could have destroyed lithium-7 as it was being formed, or maybe the rates of the known reactions that produce it have subtle errors that become significant at the precision we're now demanding. Another fascinating possibility involves the stellar environments themselves. Could these ancient stars, over their billions of years of life, have somehow processed and destroyed their surface lithium? Some models suggest that as these stars slowly rotate, their internal currents could drag the surface lithium down into hotter interior regions where it would be fused into heavier elements, effectively hiding the evidence from our telescopes. However, finding a stellar mechanism that reliably removes exactly the right amount of lithium across a wide variety of ancient stars has proven to be a significant challenge. Then we venture into the realm of more exotic explanations, where the lithium problem becomes a potential portal to new physics. What if an unknown type of particle, left over from the very early universe, was present during those first few minutes? Certain theoretical candidates for dark matter, for instance, could have decayed or annihilated during or shortly after BBN. The energy and particles released from such decays could have disrupted the delicate nuclear chain reactions, selectively destroying lithium-7 nuclei without significantly affecting the other elements. This would be a breathtaking discovery, as it would mean that the fossilized nuclear ash from the Big Bang itself contains the fingerprint of dark matter. Alternatively, the discrepancy could be a hint that the fundamental constants of nature, like the strength of the gravitational force, were slightly different during the BBN epoch than they are today. A small change could have shifted the nuclear Chinese letter enough to suppress lithium production. The lithium problem, therefore, is far more than a minor accounting error in the cosmic ledger. It represents a direct and unresolved tension between our well-tested model of the universe's first light and the tangible chemical fossils we find in its oldest stars. It forces us to question whether we fully understand the nuclear processes of the Big Bang, the evolution of the first stars, or if we are being guided by this missing lithium toward a deeper layer of reality, one populated by exotic particles and fundamental constants that are not quite as constant as we once believed. Just as we begin to feel we're accounting for the universe's large-scale oddities, we are confronted with a problem so acute and so precisely measured that it threatens to unravel the very fabric of modern cosmology. This is the Hubble Tension, a disagreement over one of the most fundamental numbers in all of physics, the Hubble constant, or H0. This number represents the current expansion rate of our universe, telling us how fast galaxies are receding from us for every megaparsec of distance. Determining this value is perhaps the closest thing cosmology has to a holy grail, as it sets the age, size, and ultimate fate of the cosmos. And right now, we have two supremely confident, exquisitely precise methods of measurement that are giving us two distinctly different answers. It's as if you used two impeccably calibrated clocks to time the same event, and one insists it took 1 minute, while the other just as confidently states it took 1 minute and 5 seconds. The difference seems small, but the implications are colossal. One method takes what we might call the local route. Astronomers use a cosmic distance ladder, a series of interconnected steps, to measure the expansion rate directly in our cosmic neighborhood. It starts with celestial landmarks we understand well, like Cepheid variable stars. These stars pulse at a rate that is directly tied to their intrinsic brightness. By measuring their pulsation period, we know their true luminosity. Comparing that known brightness to how dim they appear from Earth gives us a direct measurement of their distance. We then use these Cepheids located in nearby galaxies to calibrate the next step on the ladder, Type Ia supernova. These stellar explosions are even brighter, visible across billions of light years, and they have a remarkably consistent peak brightness. Once calibrated by the Cepheids, these supernovae become what astronomers call standard candles. By observing how much these distant supernovae have redshifted, stretched to longer wavelengths by the expansion of space, and comparing that to their distances, we get a direct local measurement of the Hubble constant. This painstaking work, led by teams like the one using the Hubble Space Telescope, yields a value around 73 kilometers per second per megaparsec, with an uncertainty of just about 1%. Meanwhile, a completely different approach looks back to the very beginning, using the cosmic microwave background as the ultimate standard ruler. This method doesn't measure the universe's current expansion directly. Instead, it uses a snapshot of the infant cosmos to predict what the expansion rate must be today, based on our best model of cosmic evolution, the lambda cold dark matter model. The CMB map is not just a collection of random hot and cold spots. It's a frozen record of acoustic oscillations, the sound waves that were traveling through the primordial plasma. The physical scale of these waves is set by a fundamental quantity: how far a sound wave could travel from the Big Bang until the universe became transparent. This distance is imprinted on the CMB as a characteristic peak in the statistical distribution of the spots, a preferred angular size. By measuring this angular size on the sky with incredible precision, missions like Planck can work backward. They know the actual physical size of this standard ruler, and by seeing what angle it subtends in the sky, they can calculate the geometry of the universe and, consequently, the Hubble constant. This pristine early universe method points to a value of about 67.4 kilometers per second per megaparsec, also with a sub-1% margin of error. The problem is stark: 73 versus 67.4, a gap of nearly 6 kilometers per second per megaparsec. Now, in many scientific contexts, a difference of less than 10% might not seem like much. But in the world of precision cosmology, where both measurements have uncertainties below 2%, this discrepancy is enormous. We're not talking about a slight overlap in the error bars. The two values are separated by a chasm of over 4 sigma. In statistics, a 4 sigma result means the probability that this disagreement is just a random fluke is less than 1 in 16,000. This isn't a minor quibble, it's a fundamental crisis. It suggests that one of our most trusted measuring rods is broken, or worse, that our entire understanding of cosmic history, the lambda CDM model, is missing a crucial ingredient. This tension forces cosmologists to consider truly revolutionary possibilities. What if there is physics beyond our current standard model that played a role in the early universe? One compelling idea is early dark energy. We already include dark energy in our models to explain the universe's accelerated expansion today. But what if a similar form of energy was also active in the first few 100,000 years after the Big Bang? This extra early dose of repulsive gravity would have subtly altered how the universe expanded during that critical period. It would change the journey of those primordial sound waves, effectively making the standard ruler from the CMB a slightly different size. When we plug this modified early history into our models, the predicted Hubble constant today shifts upward, potentially bridging the gap toward the higher value measured by the supernova. Early dark energy acts as a cosmic adjuster, tweaking the universe's infancy to match its observed adulthood. Another avenue of investigation points to the ghostly neutrino. The standard model of particle physics assumes these particles have negligible mass, but we now know they have a tiny, non-zero mass. What if their properties are more exotic than we think? Perhaps there is an additional, sterile type of neutrino that doesn't interact via any force except gravity. Or maybe the number of neutrino families or their effective mass was different in the early universe. Changes to the neutrino sector would affect the timing of key events in cosmic history, like the onset of the formation of large-scale structure. Since the CMB is exquisitely sensitive to the timing of these events, altering the neutrino properties would change the model's inference for the Hubble constant. This would mean the resolution to the Hubble tension lies not in a new form of energy, but in a deeper understanding of the most elusive known particles in existence. Of course, the more conservative explanation is that there is an unaccounted for systematic error in one of the measurement campaigns. Perhaps the cosmic distance ladder has a hidden rung that is slightly warped. Maybe our understanding of Cepheid stars or Type Ia supernova is not as universal as we thought, and they evolve over cosmic time in ways we haven't fully calibrated. Teams on both sides of the tension are relentlessly checking and rechecking their data, searching for any potential oversight. Yet, as the measurements become more and more precise, the discrepancy not only persists but seems to solidify. The Hubble tension, therefore, is more than just a technical dispute over a number. It is a profound reminder that our maps of the cosmos, from the ancient light of the CMB to the exploding stars in our galactic backyard, are telling a story that is still unfolding. The universe is presenting us with a clear, quantitative inconsistency, a direct challenge to our models that may very well be the first undeniable clue leading us to the next great revolution in our understanding of physics. As we trace the journey of this ancient light across billions of years, we must consider that its path was not a perfectly straight line. The fabric of space-time, warped by all the matter and energy in the universe, acts like a vast, complex lens. This brings us to the subtle but significant mystery of gravitational lensing in the cosmic microwave background. When the photons of the CMB began their epic voyage, they were emitted from the surface of last scattering with a specific pattern of hot and cold spots, a pristine imprint of the infant universe's density variations. But as these photons traveled toward us, they didn't move through empty, flat space. They passed by galaxies, vast clusters of galaxies, and enormous clouds of dark matter. According to Einstein's theory of general relativity, any concentration of mass bends the very space around it. So, when a CMB photon skirts the edge of a massive object, its path is subtly deflected, much like a beam of light is bent when it passes through a glass lens. This cosmic phenomenon is known as gravitational lensing. This lensing doesn't create new hot or cold spots. Instead, it gently smears and reshuffles the existing ones. It takes the original, sharp fingerprint of the early universe and adds a soft, blurring filter over it. The effect is incredibly faint. The temperature changes it induces are minuscule, but with the exquisitely sensitive, full-sky maps from the Planck satellite, scientists have developed sophisticated statistical tools to detect this smoothing effect. By studying how the lensing subtly correlates the temperatures at different points, they can reconstruct a map of the total matter, including the invisible dark matter that caused the lensing along the entire line of sight. It's a remarkable achievement, using the distorted baby picture of the universe to chart the distribution of all the cosmic scaffolding that formed after the picture was taken. According to our standard lambda cold dark matter model, the amount of lensing we should see can be predicted based on the primary temperature fluctuations themselves. The model provides a very specific expectation for how much this cosmic blurring should have occurred. Here is where the anomaly emerges. When the Planck team meticulously measured the actual lensing signal imprinted on the CMB, they found it was stronger than expected. The observed blurring effect is about 7% more powerful than the prediction derived from the primary CMB fluctuations within the lambda CDM framework. A 7% excess might not sound like much, but in the world of precision cosmology, where measurements often have uncertainties of less than 1%, this discrepancy is notable, sitting at a confidence level of around 2 to 3 sigma. This means there's only about a 1 in 50 chance that this is a random statistical fluctuation. It suggests that the universe is lensing the CMB light more effectively than our best model says it should. The cosmic lens seems to be slightly stronger than we thought. What could be causing this extra lensing power? One compelling explanation points to the clustering of matter. The lensing signal is a direct measure of the total clumpiness of matter in the universe. If matter is more clustered, if it has gathered into denser knots and filaments than our standard model predicts, then it would create stronger gravitational potentials, bending the paths of CMB photons more significantly and producing the observed excess. This would mean that the cosmic web, the vast, invisible structure of dark matter that guides the formation of galaxies, is more pronounced and lumpy than we have accounted for. This idea intersects with other cosmological probes. Some measurements of how galaxies cluster in the local universe also seem to suggest a slightly higher level of clumpiness than is inferred from the primary CMB. The lensing anomaly could therefore be another piece of evidence pointing toward a consistent, unresolved tension in our understanding of how structure forms. Another, more radical possibility is that this anomaly is a hint that our theory of gravity itself needs modification on the largest scales. Einstein's general relativity has passed every test with flying colors within the solar system and in binary pulsar systems. But its behavior across the vast expanse of the cosmos, dominated by dark energy and dark matter, is less certain. What if gravity operates in a slightly different way over these immense distances? Modified gravity theories, such as those known as FR gravity or Mond-like extensions, propose that the force of gravity strengthens in regions of extremely low acceleration, like the voids between galaxy clusters. Such a modification could enhance the gravitational lensing effect caused by large-scale structures, creating a stronger smearing of the CMB without requiring extra matter. The lensing anomaly thus becomes a potential experimental foothold for these alternative theories, a faint signal that the rules governing the cosmos might be more complex than Einstein's beautiful, yet potentially incomplete equations. A third avenue considers the nature of the neutrinos streaming through the universe. If these ghostly particles have a larger total mass than we currently estimate, they would have slowed down earlier in cosmic history, contributing more effectively to the gravitational potential of forming structures. This enhanced gravitational pull would also lead to a stronger lensing signal. Alternatively, if there were additional sterile neutrino species, they would add to the radiation density in the early universe, altering the growth of structures and potentially amplifying the lensing we observe today. The subtle excess in the CMB's blurring could therefore be a clue not about dark matter's distribution, but about the properties of the most elusive known particles. The lensing anomaly, while a quiet and statistical mystery, connects deeply to the most fundamental questions in physics. It challenges us to determine whether we need more stuff in the universe, a different kind of stuff, or a completely new set of rules for how gravity assembles the cosmic architecture that shapes the journey of light itself. But as we try to listen to the universe's faintest whisper, we face a monumental challenge. The cosmos is a very noisy place. This brings us to our 13th mystery, the confounding puzzle of point source foregrounds. Imagine you're an audio engineer trying to record the delicate song of a single, rare bird in the middle of a dense, cacophonous jungle. The bird's call is the primordial signal of the cosmic microwave background, but the jungle is filled with the chirps, croaks, and roars of countless other creatures. In cosmology, these other creatures are the foregrounds, everything between us and the surface of last scattering that also emits microwave light, threatening to drown out the main event. The most persistent of these distractions are unresolved point sources, distant galaxies, blazing quasars, and other energetic objects that are so far away they appear as mere pinpricks of light, even to our most powerful telescopes. Each of these objects is a powerful radio transmitter, and their combined emission blends seamlessly into the CMB map, creating a background static of localized heat that can mimic or obscure the subtle temperature variations we're desperate to study. The process of cleaning this data is a monumental task. Satellites like Planck don't just look at the sky in one color of microwave light. They scan it across multiple frequencies from around 30 GHz to over 800 GHz. This is the key to the entire operation. The true CMB has a very specific blackbody spectrum, meaning its brightness follows a predictable curve across these different frequencies. Foreground emissions, however, have their own distinct spectral signatures. The diffuse gas and dust of our own Milky Way galaxy, for instance, glows with a different character. Synchrotron radiation from electrons spiraling in galactic magnetic fields is brightest at lower frequencies, while interstellar dust heated by starlight shines most brightly at the higher end of the spectrum. The point sources, those distant galaxies and quasars, add another layer of complexity, each with its own unique spectral fingerprint based on its internal physics. Cosmologists must become master chefs, carefully following a cosmic recipe to separate these overlapping ingredients. They use sophisticated algorithms to analyze the multi-frequency maps, identifying the contribution of each foreground component based on its known spectral behavior, and then subtracting it away layer by layer, hoping to be left with the pristine CMB underneath. The great mystery and risk here is that this subtraction can never be perfect. It's an incredibly delicate operation, and even a tiny misstep can leave behind residuals, faint imprints of the foregrounds that masquerade as genuine features of the primordial CMB. This leads to a deeply unsettling possibility. What if some of the profound anomalies we've already discussed, like the cold spot or the hemispherical power asymmetry, aren't features of the Big Bang at all? What if they are instead mere ghosts in the machine, artifacts created by an incomplete or slightly inaccurate removal of these local point sources? A cluster of particularly bright, unresolved radio galaxies in one part of the sky, if not perfectly accounted for, could create a pattern that looks like a large-scale cold anomaly. Similarly, an uneven distribution of galactic dust emission could theoretically produce a false impression of a power asymmetry across the sky. The haunting question for cosmologists is whether they are studying the universe's birth certificate or a cleverly altered forgery, where the ink of local structure has bled through the ancient parchment. This uncertainty fuels an ongoing, high-stakes effort to observe the sky with ever greater resolution and frequency coverage. The goal is to resolve the unresolvable, to detect and catalog every single significant point source down to fainter and fainter limits, so they can be meticulously subtracted. New ground-based telescopes and future space missions are being designed with this specific challenge in mind. They aim to provide such a sharp, multicolored view of the microwave sky that the foregrounds can be mapped with near-perfect precision, allowing for a cleaner extraction of the CMB signal than ever before. Yet, this process itself reveals a deeper layer of the mystery. The point sources aren't just noise, they are a fascinating population of objects in their own right. Many of them are incredibly distant, meaning we are seeing them as they were billions of years ago. Their distribution and properties tell a parallel story about the formation and evolution of galaxies and supermassive black holes across cosmic time. So, in our quest to remove these foregrounds to see the beginning, we are simultaneously building an invaluable record of everything that came after. The struggle to distinguish the singer from the song of the jungle is, in the end, a fundamental part of understanding the complex and layered history of our cosmos. While we've been exploring the strange symmetries and asymmetries imprinted on the ancient cosmic light, there is one feature so prominent and so clear that it was detected even before the CMB's uniform background was discovered. This is the cosmic dipole, and at first glance, its explanation seems straightforward and settled science. The entire sky map of the cosmic microwave background is not perfectly uniform. It has a distinct gradient, a kind of cosmic slope. One half of the sky appears very slightly warmer, while the opposite half appears correspondingly cooler. The difference is minute, only about 1 part in 1,000, but it's the single largest anisotropy in the entire CMB. For decades, the accepted explanation for this has been our own motion. Our solar system, our galaxy, our entire local group of galaxies is not standing still relative to the cosmic rest frame defined by the CMB. We are rushing through space at an incredible speed of about 370 kilometers per second. This motion creates a familiar physical effect known as Doppler boosting. Just as the sound of an ambulance siren pitches up as it moves toward you and down as it moves away, the CMB photons we are flying toward appear boosted in energy, making that region of the sky seem warmer. Conversely, the photons we are racing away from appear redshifted and cooler. This kinematic dipole is in essence our own reflection in the cosmic mirror, a fingerprint of our local journey through the expanding universe. But what if this simple, elegant explanation isn't the whole story? A profound and unsettling mystery is now emerging from the depths of the data. When cosmologists use the observed motion of distant galaxies and galaxy clusters to independently calculate what our kinematic dipole should be, they are finding a potential discrepancy. The amplitude and direction of the dipole we see in the CMB might not perfectly match the dipole we would expect from our measured velocity alone. This raises a breathtaking possibility. What if a part of this dominant signal is not due to our motion at all, but is instead an intrinsic feature of the cosmic microwave background itself? It would mean that the universe's oldest light carries within it a fundamental lopsidedness, a built-in gradient from the moment of its birth. The implications of such a discovery would be nothing short of earth-shattering. It would directly violate the cosmological principle's tenet of isotropy, suggesting that the universe has a preferred direction on its largest possible scale from the very beginning. We wouldn't just be seeing our own motion, we would be seeing the universe itself tilted, like a floor that slopes gently in one universal direction. Separating these two potential dipoles, our own kinetic signature from a possible primordial one, is a task of almost unimaginable difficulty and profound consequence. Think of it like trying to hear a single, quiet instrument playing a sustained note while you're riding on a speeding train with the wind roaring in your ears. The roar of the wind is our kinematic dipole, loud and clear. The faint, steady note is the hypothesized intrinsic dipole. To isolate it, scientists are turning to other cosmic tracers. They look at the distribution of distant quasars and radio galaxies across the sky. The logic is this: if the entire CMB dipole is purely due to our motion, then this same motion should also impart a similar Doppler effect on the number counts of these distant objects. As we move toward one direction, we should see slightly more galaxies in that part of the sky due to relativistic effects, and fewer in the opposite direction. Recent surveys, however, have begun to hint that the dipole in the distribution of these millions of quasars might be larger than what our measured motion predicts. This is a hint that the roar of the wind might be masking a real cosmic note, that part of the signal is indeed intrinsic to the universe's structure. If this is confirmed, it would force a radical rewrite of our cosmic story. An intrinsic dipole could be a relic from the epoch of inflation, a sign that the inflationary field that blew up the universe was not perfectly uniform but had a slight tilt or gradient. This would mean that the seeds for all cosmic structure were planted on a foundation that was already fundamentally lopsided. Alternatively, it could point toward an even more exotic scenario, such as our universe being part of a larger multiverse where our bubble universe resides in an anisotropic background, imprinting its grander geometry onto our local CMB. The painstaking work to confirm or refute this idea is at the very cutting edge of cosmology. requiring ever larger catalogues of distant objects and ever more precise modeling of subtle relativistic effects. The cosmic dipole, once thought to be a simple marker of our own journey, has become a potential window into the deepest and most fundamental nature of the cosmos, challenging the very principle that we do not live in a special place in a universe that is the same in every direction. Now, to truly hear the faintest whispers of the universe's birth, we must learn to see its ancient light in a new way, not just as a map of temperature, but as a canvas of polarized light. This brings us to our 15th mystery, a realm where the CMB reveals its hidden textures through the phenomenon of polarization. Think of the CMB photons not just as carriers of heat, but as individual waves of light, each one vibrating in a specific direction. When this light was finally set free during recombination, it was scattered for the very last time by the electrons in the primordial plasma. This final interaction left a distinct imprint on the light, polarizing it in a way that encodes a breathtaking amount of new information about the universe's first moments. It's like moving from a simple black and white photograph to a full-color, three-dimensional movie with a detailed soundtrack. The polarization of the cosmic microwave background is that soundtrack, and it tells a story of turbulent motion in the infant cosmos. To understand this, we need to distinguish between two fundamental patterns in this polarized light, known rather technically as E modes and B modes. Imagine you're looking at a pattern of arrows on a flat surface, each arrow showing the direction of the polarization. An E-mode pattern looks like the electric field around positive and negative charges. The arrows seem to radiate outward from central points or flow inward toward them. It has a kind of radial or convergent quality, like the petals of a flower or the magnetic field lines around a simple bar magnet. These E-modes are primarily generated by the chaotic, random motions of the hot plasma in the early universe, the same density variations that created the hot and cold spots in the temperature map. They are a vital piece of the puzzle, but they largely confirm the story we already know from the temperature fluctuations. The B modes, however, are the real holy grail. Their pattern is fundamentally different. It has a swirling, curling character, like the pattern of water draining from a sink or the twisting of a towel. This curl is the crucial signature. While weak B modes can be created later by the gravitational lensing of E modes as the CMB light passes by cosmic structures, the most sought-after signal is that of primordial B modes. These would be a direct, fossilized imprint of gravitational waves from the epoch of cosmic inflation. Gravitational waves are ripples in the very fabric of spacetime itself, predicted by Einstein and now detected from colliding black holes. But the ones produced during inflation would be on a completely different scale, cosmic tsunamis generated as the universe underwent its violent, exponential expansion. The detection of these primordial B modes would be the ultimate smoking gun, providing direct, incontrovertible evidence for cosmic inflation and opening a direct window into the universe when it was a mere fraction of a second old. It would allow us to probe energy scales 1 trillion times higher than anything we can reach with particle accelerators on Earth. This has sparked one of the most intense and technically heroic hunts in the history of science. Teams across the globe have built incredibly sensitive telescopes in some of the most remote and pristine environments on Earth. The high, dry plateaus of the Atacama Desert in Chile and the frigid, thin air of the South Pole. These locations are chosen because the Earth's atmosphere is largely transparent to the specific microwave frequencies they need to measure. The goal is to stare at a patch of sky with painstaking patience, filtering out every possible contaminant, hoping to catch a glimpse of that faint, swirling pattern imprinted on the polarized light from the dawn of time. The potential prize is so monumental that it drives physicists to push the very limits of technology. Yet, this grand search has been plagued by confounding obstacles and tantalizing, but ultimately unconfirmed signals. The primary challenge is that the primordial B-mode signal is incredibly faint. estimated to be more than 1,000,000 times weaker than the dominant temperature fluctuations. And this whisper is buried under two incredibly loud and persistent sources of noise. The first is the gravitational lensing we discussed earlier. As the CMB photons travel for billions of years, the gravitational pull of all the matter in their path subtly distorts the polarization pattern itself. This process takes the relatively straightforward E modes and twists them, converting a portion of them into a background of what's called lensing B modes. This creates a fog that completely obscures the faint primordial signal for all but the very largest angular scales. Cosmologists are now developing advanced techniques, often called delensing, to create a map of this fog and subtract it from their data, but it is a Herculean task. The second major contaminant comes from our own cosmic backyard, galactic dust. Our own Milky Way is filled with microscopic, elongated dust grains that are aligned by the galaxy's magnetic field. These spinning dust particles emit their own polarized light in the microwave range, and they also produce a pattern that has both E mode and B mode characteristics. This galactic foreground is not a uniform haze. It is a complex filamentary tapestry that varies dramatically across the sky. In some regions, its signal can be thousands of times stronger than the primordial B modes we are trying to detect. This was starkly demonstrated in 2014 when the BICEP 2 team announced the possible detection of primordial B modes, only to find out in a joint analysis with the Planck satellite that the signal they saw could be entirely explained by polarized dust emission from our own galaxy. It was a sobering lesson in the perils of foreground contamination. This ongoing struggle leaves one of the biggest questions in all of physics unanswered. What is the true energy scale of inflation? The amplitude of the primordial B-mode signal is directly tied to the energy at which inflation occurred. A strong detection would tell us that inflation was a high-energy event, happening at a scale that unifies all the fundamental forces. A non-detection after an exhaustive search would push the energy scale lower, ruling out many of the most popular and elegant inflationary models. The fact that we have not yet made a definitive detection, despite over a decade of dedicated searching with ever more sensitive instruments, is itself a profound result. It is forcing theorists to reconsider the landscape of possible inflationary scenarios. The elusive nature of these primordial swirls in the cosmic light is a constant reminder that the universe guards its deepest secrets closely, and that every new window we open onto the cosmos reveals not only answers, but a new set of even more challenging and compelling mysteries. While the CMB gives us a pristine baby picture of the universe, the story doesn't end there. The cosmos grew up, and its adolescence and adulthood are written in the vast cosmic web of galaxies that stretches across billions of light years. This large-scale structure is the direct descendant of the tiny density fluctuations we see frozen in the CMB. The gravity of those slightly denser patches slowly pulled in more and more matter over billions of years, eventually forming the glittering filaments and clusters we map today. To understand this entire cosmic movie from the first frame to the present day, we need to connect that ancient baby picture to the universe we see now. This is where a subtle but powerful geometric test comes into play, known as the Alcock-Paksinski effect, and it's at the heart of our 16th mystery, one that reveals a potential crack in our timeline of cosmic evolution. The Alcock-Paksinski effect is a clever way to measure the shape and expansion history of the universe using the large-scale structure itself as a standard ruler. Imagine you're looking at a distant spherical cloud of galaxies. You can measure its size in two different ways, across your line of sight and along your line of sight. The size across your line of sight is measured by its angular size on the sky, how many degrees it spans. The size along your line of sight, however, is measured by the spread in the galaxy's redshifts, which tells us how deep the cloud is. In a universe with the correct cosmological model, these two measurements should give you the same answer for the cloud's true physical diameter. The sphere should look like a sphere. But if we have the wrong model for how the universe has expanded, the sphere will appear distorted. It might look squashed along the line of sight or stretched sideways. This is because the conversion from angular size to physical size depends on the geometry of the universe, while the conversion from redshift spread to physical size depends on the expansion rate history. By studying the apparent shapes of these vast isotropic structures, we can essentially test our cosmic model. The CMB provides the initial conditions and a prediction for how this large-scale structure should look. Galaxy surveys like the Sloan Digital Sky Survey then go out and measure its actual appearance, using the Alcock-Paksinski effect to calibrate the cosmic ruler. This is where the mystery deepens. When scientists perform this meticulous comparison, they are finding hints of a discrepancy. The growth of cosmic structure inferred from the CMB, the predicted strength and clumpiness of the galactic web, seems to be in slight tension with the growth measured directly in the large-scale structure of the local universe. In simple terms, the universe appears to be slightly smoother and less clumpy today than our best lambda cold dark matter model, calibrated by the pristine CMB, says it should be. The CMB predicts a certain level of gravitational collapse and galaxy clustering over 13 billion years, but our telescopes are seeing a cosmos that is a bit more diffused. This isn't a dramatic, glaring error, but a persistent, low-level statistical tension that, like the Hubble tension, refuses to go away with more data. It's as if we had a detailed forecast for a storm predicting how much rain would fall, but when we go out with our gauges, we find the rainfall was noticeably lighter. Something seems to be suppressing the growth of structure, putting a gentle brake on the universe's natural tendency to clump together under gravity. So, what could be applying this cosmic brake? One of the most exciting possibilities involves a new property of dark energy. In the standard model, dark energy is the cosmological constant, a steady, unchanging form of energy inherent to the vacuum of space. But what if dark energy is not constant? What if it's dynamic, a field that has evolved over time? This idea is known as quintessence. If dark energy was stronger in the recent cosmic past, its repulsive gravity could have started opposing the growth of structure earlier than we think. Gravity pulls matter together to form galaxies and clusters, while dark energy's repulsive push works to pull them apart. A dynamic dark energy that ramped up its influence would have put an early end to the party, preventing matter from clustering as much as our models predict. The slight smoothness we see in the large-scale structure could be the direct signature of this evolving dark energy, a fundamental shift in our understanding of the force that dominates the cosmos. Another profound explanation points not to dark energy, but to the laws of gravity themselves. Einstein's theory of general relativity has been spectacularly successful, but its validity across the entire universe is an assumption. The growth of structure is exquisitely sensitive to how gravity works on the largest scales. If gravity behaves differently in the vast, low-density voids between galaxy clusters than it does in our solar system, it could easily account for the observed suppression of clustering. Theories of modified gravity, such as those that add new terms or functions to Einstein's equations, can naturally produce a slower rate of structure formation. In this view, the discrepancy is not caused by a new form of energy, but by our incomplete understanding of the fundamental force that has shaped the cosmos. The large-scale structure is thus a testing ground for the very laws of physics, and its subtle smoothness could be the first hard evidence that we need to rewrite Einstein's textbook. The resolution to this puzzle is one of the primary goals of a new generation of astronomical observatories. We are on the verge of a golden age of cosmic cartography, with missions like the Euclid Space Telescope and the ground-based Vera C. Rubin Observatory coming online. These are not merely telescopes, they are cosmic demographers designed to map the three-dimensional positions and shapes of billions of galaxies across an immense volume of the universe and back through a significant fraction of cosmic time. The Rubin Observatory, with its mammoth camera, will repeatedly scan the entire southern sky, providing an unprecedented movie of the cosmos. Euclid, from its stable position in space, will measure the shapes of galaxies with exquisite precision to trace the dark matter that lenses their light. Together, they will measure the Alcock-Paksinski effect with a precision that is unimaginable today. They will provide a definitive, three-dimensional map of the cosmic web, allowing us to measure the growth of structure directly and compare it with the CMB's prediction with minimal uncertainty. This powerful synergy between the ancient light of the Big Bang and the vibrant structure of the modern universe will either solidify our standard model of cosmology or finally break it, guiding us toward a new understanding of dark energy, gravity, and the ultimate fate of everything we see. However, pinning down the exact timeline of this cosmic dawn has proven to be incredibly difficult, leading us directly into our 17th mystery, a subtle but crucial conflict known as the Tau tension. This mystery revolves around a single, powerful parameter measured from the CMB's polarization, the optical depth to reionization denoted by the Greek letter tau. In essence, tau tells us how much the ancient CMB light was scattered by free electrons during the reionization era. A higher tau value means there were more electrons along the line of sight, suggesting that reionization started earlier and was a more drawn-out process. A lower tau implies a later, quicker reionization. It's a direct, if indirect, probe of the very first generations of stars and galaxies, telling us when they collectively became powerful enough to flood the cosmos and permanently change its fundamental state. The tension arises because our measurements of tau have been telling two different stories. The initial analysis of the data from the Planck satellite pointed toward a relatively low tau value. This suggested a picture where reionization was a late and rapid event, starting around when the universe was roughly 450 million years old and concluding by the time it was 1 billion years old. In this scenario, the first stars and galaxies took their time to build up and spread their ionizing influence, a more gradual cosmic awakening. This was a comfortable result as it aligned well with what some early galaxy surveys were showing. We simply weren't finding many bright, early galaxies that could have powered a much earlier reionization. But then the puzzle deepened further. More refined analyses of the very same Planck data, using different statistical techniques and paying closer attention to how foregrounds like galactic dust were removed, began to hint at a higher value for tau. This revised figure paints a dramatically different picture. Reionization may have started much earlier, perhaps when the universe was only 200 million years old. This pushes the dawn of the first luminous objects back into a far more ancient and obscure epoch. The implications are profound. An earlier reionization means the first stars and galaxies must have formed earlier and in greater numbers than we had previously believed. They had to be exceptionally efficient at producing the intense ultraviolet radiation needed to rip electrons away from hydrogen atoms. This creates a significant challenge for our models of early structure formation. Where are all these incredibly early, bright galaxies? Our deepest Hubble Space Telescope images struggle to find them in sufficient numbers to account for such an early tau, creating a potential crisis for our understanding of the universe's first chapters. The reason this timeline is so hard to pin down is that tau is an integrated measure. It tells us the total amount of scattering that happened, but it doesn't provide a detailed movie of how that scattering was distributed over time. It's like knowing the total rainfall for a year, but not whether it came from a few heavy storms or many months of drizzle. The CMB polarization data gives us the final tally, but it's difficult to deconstruct the exact history from that single number. This is where independent observations become critical. astronomers use giant ground-based telescopes to peer at the most distant quasars. By analyzing the absorption lines in their light, they can see how much neutral hydrogen is left in the intergalactic medium at different cosmic times. These observations largely suggest that reionization was mostly complete by the time the universe was about 1 billion years old, which seems to favor the later, lower tau scenario. But if tau is indeed higher, it means the very beginning of this process was lost in the deeper shadows of time before the earliest quasars we can currently see. This tension is far more than a technical disagreement over a decimal point. It strikes at the heart of how we understand the formation of the very first structures in the cosmos. A higher tau forces us to consider that the first stars might have been fundamentally different from those we see today, perhaps incredibly massive, luminous, and short-lived population Roman 3 stars that blazed with an intensity never seen since. Alternatively, it might suggest that early galaxies were far more efficient at leaking their ionizing radiation into intergalactic space than our current models allow, or that other, more exotic sources like accreting supermassive black holes played a much larger role than we thought. The ongoing quest to resolve the tau tension is a driving force behind the next generation of astronomical observatories. The James Webb Space Telescope, with its unprecedented power to see the first galaxies, is directly searching for the population of early, bright objects that could have powered a swift reionization. By counting these ancient galaxies and measuring their properties, Webb is providing the crucial, direct evidence needed to anchor our interpretation of tau. The final resolution of this mystery will write the definitive timeline for the end of the cosmic dark ages, revealing the true nature of the first celestial beacons that forever illuminated the cosmos. We've already encountered the puzzle of the universe's flatness, a mystery of staggering fine-tuning that cosmic inflation elegantly resolved, but the story doesn't end there. With the advent of modern, space-based observatories, we haven't just accepted that solution. We've put it to the ultimate test, using the cosmic microwave background as a cosmic carpenter's level to check the geometry of our entire reality. The primary tool for this is the CMB power spectrum, that intricate graph of peaks and troughs that represents the different harmonics of the universe's primordial sound waves. The precise position of the very first peak, in particular, is exquisitely sensitive to the overall geometry of space. In a positively curved universe resembling the surface of a sphere, parallel light rays would converge, making the same physical feature appear larger on the sky. In a negatively curved, saddle-shaped universe, those light rays would diverge, making objects appear smaller. But in a perfectly flat universe, the rays travel in straight lines, and the angular size we measure directly reflects the true physical size of the feature. When we analyze the data from the Planck satellite with this in mind, the result is breathtakingly clear. The first acoustic peak sits almost exactly where it should for a universe with zero spatial curvature. The data aligns with a flat geometry to an astonishing precision, constraining the curvature parameter to be within just a few hundredths of a percent of zero. This is not a rough estimate, it's a measurement of phenomenal accuracy, telling us that if the universe is curved at all, the radius of that curvature is far, far larger than our entire observable horizon. For all intents and purposes, as far as we can see, the cosmos is flat. This finding is a monumental triumph for the inflationary paradigm, as inflation's relentless stretching was the very mechanism predicted to drive the universe toward this precise geometric state, no matter what its initial shape might have been. Yet within this triumphant confirmation lies a subtle, lingering enigma. While the data is perfectly consistent with a universe that is exactly flat, our measurements, no matter how precise, always come with a margin of error. The current data doesn't rule out a curvature that is infinitesimally small, but not quite zero. Imagine measuring the flatness of a seemingly perfect marble floor with a laser level so sensitive it could detect a slope the height of a single atom across a football field. Our current cosmological instruments are that sensitive, and they tell us the floor is flat too within that incredible tolerance, but they cannot prove it is perfectly flat for all eternity. There remains a tiny, allowable window for the universe to have a minuscule positive or negative curvature. This sliver of uncertainty is the seed of a profound mystery. What if, in the future, with a next-generation CMB experiment possessing even greater sensitivity, we were to peer into this window and find that the curvature is not zero after all? The implications would be nothing short of revolutionary, forcing a major revision of our most cherished cosmological stories. A definitive detection of even a tiny amount of positive curvature would suggest a cosmos that is finite and closed like the surface of a four-dimensional sphere. While still unimaginably vast, such a universe would have a finite volume with no discernible edge. This would radically alter our understanding of the universe's ultimate fate and its global structure. More importantly, it would deliver a severe blow to the simplest models of cosmic inflation. The most straightforward versions of inflationary theory don't just predict a nearly flat universe. They drive the curvature so exponentially close to zero that detecting any deviation would be virtually impossible. Finding a measurable curvature would mean that inflation either didn't happen, or that it was a far more complex and nuanced event than we currently envision, perhaps one that didn't last quite long enough to completely iron out all the primordial wrinkles, leaving behind a faint but detectable signature of a pre-inflationary curvature. Conversely, a measurement confirming a tiny negative curvature would point toward an open, saddle-shaped universe that stretches into infinite hyperbolic space. This, too, would challenge the inflationary narrative and could point toward exotic physics at the dawn of time, such as a different type of inflationary field or an initial condition that was profoundly different from what we assume. The ongoing quest to measure the universe's curvature with ever greater precision is therefore not just an exercise in dotting the I's and crossing the T's. It is a direct probe of the universe's global shape and a fundamental test of the inflationary paradigm itself. The fact that our most precise data still leaves that door open just a crack means that one of cosmology's most basic questions, the true, large-scale geometry of our cosmic home, remains, in its most profound sense, an active and thrilling mystery. Taking a step back from these individual enigmas, we arrive at one of the most profound and overarching questions in all of modern cosmology. When you look at them one by one, each anomaly can often be explained away as a rare but possible statistical fluke. But when you line them all up, the lopsided axis of evil, the too cold spot, the imbalanced hemispherical power asymmetry, the missing large angle correlations, the unexpected lensing strength, and the potential hint of an intrinsic dipole, you are forced to confront a chilling possibility. Could it be that these are not isolated cosmic oddities, but rather the collective symptoms of a single, deeper illness within our standard model of the universe? This is the great statistical debate that currently divides cosmologists, a high-stakes argument over whether we are seeing the first, faint tremors of a scientific revolution or merely the predictable background noise of a vast and complex dataset. To understand the conservative viewpoint, we have to dive into a powerful statistical concept known as the look elsewhere effect. Imagine you're searching for a rare, specific pattern like a face in a vast field of random static. If you look long enough and hard enough, you will almost certainly find something that vaguely resembles a face purely by chance. Your brain is wired to find patterns even where none exist. In cosmology, the cosmic microwave background map is an incredibly rich dataset brimming with billions of data points. When scientists analyze it, they perform millions of statistical tests, probing it for correlations, asymmetries, and unusual features at every conceivable scale and orientation. The look elsewhere effect tells us that in such a massive search, it is virtually guaranteed that a few of these tests will return a result that looks statistically significant, even if the underlying model is perfectly correct. A 1 in 1,000 anomaly might sound rare, but if you perform 10,000 different tests, you expect to find about 10 such rare events. From this perspective, the CMB anomalies are just the handful of unlikely patterns we expected to find in the cosmic static. They are the statistical ghosts in the machine, and their collective weight is an illusion because they weren't predicted as a group beforehand. We fished for them one by one in a vast ocean of data. This is not just a philosophical hand wave, it's a rigorous methodological stance. Cosmologists apply brutal statistical corrections to account for this effect. They run complex simulations of the universe based on the standard lambda-CDM model, creating thousands of fake but perfectly standard CMB skies. They then analyze these simulated maps with the exact same tools and algorithms they use on the real data. This process tells them how often a particular anomaly or a set of anomalies should appear in a universe that obeys the standard rules. If the real anomalies appear no more frequently in the actual data than they do in these countless simulated universes, then the case for new physics evaporates. For many anomalies, this is precisely what happens. Their individual statistical significance drops when properly corrected for the fact that we were effectively searching for any unusual feature, not a specific one. The cold spot, for instance, while striking, becomes less shocking when you realize we've surveyed the entire sky, and it's the coldest of many cold spots. However, the other side of the argument carries a compelling, and some would say growing, weight. Proponents of this view argue that while each anomaly on its own might be dismissed, their collective persistence is what's truly telling. It's not just that we have one or two strange results. It's that several of the most significant anomalies, the axis of evil, the hemispherical asymmetry, and the lack of large-angle correlations, all seem to point in a similar direction. They are correlated with one another, hinting at a common underlying cause, a fundamental lopsidedness in the universe. This convergence is much harder to explain away as a series of independent flukes. Think of it like a detective finding a single strange fingerprint at a crime scene. It could be a coincidence, but if they also find a misplaced fiber, a strange boot print, and a broken lock, all pointing toward the same modus operandi, the case for coincidence weakens dramatically. The anomalies are not randomly distributed problems. They are clustered around the idea that our universe is not as isotropic and statistically vanilla as the cosmological principle demands. The debate is far from settled, and the scientific process is actively working to resolve it. The next generation of CMB experiments, like the Simons Observatory and CMB-S4, are being designed with this very question in mind. They won't just collect more data, they will collect data of such phenomenal precision and clarity that the statistical uncertainties will shrink dramatically. These observatories will be able to measure the polarization and temperature of the CMB with an accuracy that makes our current maps look like rough sketches. They will provide a truly definitive test. If these anomalies are mere fluctuations, they will fade into the noise as the data improves, finally revealing the underlying standard universe we expect. But if they are real, their signatures will sharpen and solidify, becoming undeniable features etched into the cosmic fossil record. This collective mystery, therefore, represents the ultimate frontier in our quest to understand the cosmos. We are in a period of extraordinary tension, standing at a crossroads. One path leads to a comforting, if slightly boring, conclusion that our standard model is fundamentally correct and we have simply been tricked by a few cosmic mirages. The other path leads to a scientific upheaval, forcing us to rewrite the textbooks with a new understanding of inflation, dark energy, or even gravity itself. The collective whisper of these CMB anomalies is the sound of the universe challenging us, daring us to look deeper and question our most basic assumptions about the nature of reality. Of course, the universe is filled with more than just the quiet echo of its birth. It is also home to the most colossal structures imaginable, vast cities of galaxies bound together by gravity in immense clusters. To understand how these titans fit into our cosmic story, we turn to a completely different way of using the cosmic microwave background, not as a direct relic, but as a backlight to illuminate the modern universe. This technique hinges on a fascinating physical process known as the Sunyaev-Zeldovich effect, or the SZ effect for short. Imagine the CMB as a uniform, ancient canvas of light. Now picture a massive galaxy cluster, a region of space filled with hundreds or even thousands of galaxies, all swimming in an enormous cloud of superheated gas. This gas is so incredibly hot, reaching temperatures of tens of millions of degrees, that its electrons are moving at nearly the speed of light. As the faint photons of the CMB travel across the cosmos and pass through one of these clusters, they have a chance to collide with these frenetic electrons. When such a collision occurs, the photon gains a tremendous burst of energy from the much more massive electron, in a process similar to a ping-pong ball being smacked by a bowling ball. This interaction, known as inverse Compton scattering, gives the photon a significant energy boost, effectively kicking it from the microwave part of the spectrum to higher energies. The brilliance of the SZ effect lies in its unique signature. For a specific region of the sky occupied by a galaxy cluster, it creates a distinct shadow in the CMB at the lower microwave frequencies where the CMB is brightest, while simultaneously creating a bright spot at higher frequencies. This signature is almost like a cosmic barcode that is completely independent of the cluster's distance from us. Unlike traditional methods that rely on measuring a galaxy's brightness, which fades dramatically with distance, the SZ effect's strength depends primarily on the density and temperature of the hot gas in the cluster. This makes it an incredibly powerful tool for finding clusters, acting as a nearly perfect census tool that can detect massive structures all the way back to the early universe, revealing how they have grown and assembled over billions of years. By conducting large-area SZ surveys with powerful telescopes, we can essentially take a head count of the most massive galaxy clusters across cosmic time, building a timeline of their abundance. This is where our next great mystery unfolds. According to our standard lambda cold dark matter model, which is exquisitely calibrated by the primary CMB fluctuations, we can make a very specific prediction for how many of these colossal clusters should exist at different epochs in the universe's history. The model tells a story of hierarchical structure formation. Small clumps of dark matter merge to form larger ones, eventually building up the massive clusters we see today. The CMB gives us the initial conditions for this growth, and our understanding of gravity and dark energy tells us how it should proceed. However, when astronomers painstakingly count the number of truly massive clusters discovered through the SZ effect and other methods, they consistently find a shortage. There seem to be fewer of these gigantic cosmic metropolises than our premier model of the universe says there should be. It's as if we had a detailed demographic forecast predicting the number of major cities with populations over 10 million. But when we conducted a global census, we found that several of these expected megacities were simply missing. This discrepancy sends cosmologists searching for the missing giants, and the explanations they are considering would reshape fundamental physics. One compelling line of thought examines the very nature of the universe's most elusive known particles, neutrinos. The standard model of particle physics long assumed these ghostly particles were massless, but we now know they have a tiny but non-zero mass. If the total mass of neutrinos is larger than currently estimated, it could have a significant impact on the growth of the largest structures. Neutrinos, due to their high speeds, tend to stream freely out of the gravitational wells where dark matter and ordinary matter are trying to clump together. This acts as a sort of smoothing agent, suppressing the formation of the very densest knots of matter. A higher neutrino mass would mean this suppressing effect is stronger, potentially preventing some of the most massive clusters from ever forming, which could neatly explain the observed deficit. The cluster count, therefore, becomes a sensitive scale for weighing the neutrino. Another profound possibility points back to the mysterious force driving cosmic acceleration, dark energy. In the Standard Model, dark energy is represented by the cosmological constant, a steady, unchanging presence. But what if dark energy is not constant? What if it is a dynamic field, often called quintessence, that has evolved over time? If dark energy became dominant earlier in the universe's history than we think, its repulsive gravity would have started opposing the pull of gravity sooner. Since galaxy clusters are the ultimate products of gravitational collapse, an earlier onset of dark energy's influence would have put a premature brake on their growth, stunting the development of the very largest clusters. The observed shortage could be the direct fossil evidence that dark energy has a history, and its strength has not been a constant throughout cosmic time. Yet another angle considers the possibility that our understanding of the physics within these clusters is incomplete. The process of cluster formation is incredibly complex, involving not just gravity, but also violent astrophysical feedback from supernova and supermassive black holes. These energetic processes can heat the surrounding gas and even expel it from the cluster's gravitational grasp, making it harder for the cluster to continue growing. If this feedback is more efficient than our simulations currently model, it could naturally limit the upper size that clusters can achieve. Alternatively, there is the more radical proposition that our theory of gravity itself needs revision on the largest scales. Modified gravity theories that weaken the force of gravity in the vast, low-density regions between clusters could also slow down the rate at which these massive structures assemble. The persistent shortfall in the number of these cosmic giants serves as a stark reminder that the universe's grand narrative, written in the afterglow of the Big Bang and the architecture of its largest structures, may still be missing crucial chapters involving the true nature of its most mysterious components. And so we arrive at perhaps the most profound question of all, one that the cosmic microwave background has uniquely equipped us to ask, even if it hasn't given us the final answer: what is the ultimate fate of everything? For centuries, this was a question for philosophers and theologians, but the CMB has transformed it into a problem of hard, observational physics. By giving us an exquisitely precise inventory of the universe's contents, the amount of ordinary matter, the density of dark matter, and the strength of dark energy, this ancient light has handed us the cosmic rulebook. We can now plug these numbers into Einstein's equations and project the trajectory of the cosmos forward to its logical conclusion. And that conclusion is both majestic and deeply unsettling. The universe is set for an eternity of cold, lonely, and ever-accelerating expansion. This is the fate dictated by the dominance of dark energy, a conclusion written indelibly into the patterns of the CMB. But here's the true mystery, one that shifts from the data itself to its breathtaking interpretation. The CMB doesn't just tell us that dark energy exists. Its precise measurements of the cosmic geometry force us to accept that this mysterious force makes up about 70% of the entire energy budget of the universe. It is the dominant component of reality, the director of the cosmic play. In our current standard model, this dark energy is modeled as the cosmological constant, a constant, unchanging energy density inherent to the vacuum of space itself. If this is true, then the future is, in a sense, decided. The expansion will continue to accelerate, but at a steady, controlled pace. Galaxies outside our local group will be pushed away from us faster and faster, their light eventually redshifted so far that they vanish from our observable universe. The cosmos will become a vastly more isolated place, with island galaxies drifting apart in an ever-cooling, ever-darkening sea of emptiness. It's a future of a slow, dignified heat death, where the universe essentially coasts to a halt at a temperature infinitesimally above absolute zero. However, this picture rests on a colossal assumption that dark energy is truly constant, and the CMB, for all its power, cannot tell us if that assumption is correct. It provides a single, pristine snapshot of the universe at 380,000 years old. It tells us the initial conditions with stunning accuracy, but it cannot directly track how dark energy has behaved over the intervening billions of years or how it might behave in the eons to come. This is the chasm of uncertainty at the heart of our cosmic forecast. What if dark energy is not a cosmological constant? What if it is a dynamic field, something physicists call quintessence, that can change over time? This single question opens the door to futures far more dramatic and violent than a quiet heat death. Consider the most extreme possibility, the Big Rip. In this terrifying scenario, dark energy is not constant but grows in strength over time. If the repulsive force of dark energy were to become sufficiently powerful, it wouldn't just push galaxies apart, it would eventually overcome all the forces that hold structures together. First, the gravitational bonds of galaxy clusters would be torn asunder. Then, the galaxies themselves would be shredded. As the acceleration became more ferocious, stars would be ripped from their galaxies. Later, planetary systems would be pulled apart. In the final, apocalyptic moments, the force would exceed the electromagnetic bonds holding atoms together, and then even the nuclear forces within atomic nuclei would be overcome. Every molecule, every atom, every fundamental particle would be violently scattered across a space-time that is expanding faster than the speed of light, leading to a literal end of all structure. The universe wouldn't just die with a whimper, it would be annihilated in a catastrophic, fundamental unraveling of reality itself. Now, the CMB hasn't shown us that this will happen. But it has set the stage for this profound uncertainty. By precisely measuring the other ingredients in the cosmic mix, the ordinary matter and dark matter, it has highlighted the dominant, mysterious role of dark energy and framed it as the central character in the story of our fate. The pressing mystery, then, is not what the CMB has seen, but what it cannot see, the future evolution of this dominant force. Is the cosmological constant the final answer, guaranteeing a long, cold, but stable future? Or is the universe poised for a far more spectacular and violent finale? The search for the answer has become the primary mission for a new generation of telescopes like the Vera-C, Rubin Observatory and the Euclid Space Telescope, which are designed to trace the expansion history of the universe with unprecedented precision, looking for any subtle sign that dark energy is changing. They are, in effect, trying to write the final chapter of the cosmic story, a chapter that the CMB brilliantly began but could not finish on its own. But just as we grapple with the universe's ultimate fate, we must turn our attention back to its very first moments, to a conceptual chasm so profound it threatens to undermine the entire inflationary story we've been telling. This is the trans-Planckian problem, a mystery that forces us to question whether our most successful cosmological theory is built on a foundation of sand. To understand it, we need to revisit the elegant idea of inflation. This period of hyper-expansion is celebrated for taking tiny, microscopic quantum fluctuations and stretching them across the cosmos, eventually providing the gravitational seeds for all structure, from galaxies to the hot and cold spots in the CMB. It's a beautiful, compelling narrative, but if we rewind that process, following one of those fluctuations backward in time to the very start of inflation, we encounter a physical impossibility. The mathematical projection suggests that the physical wavelength of that fluctuation, the very thing that would become a vast supercluster, was once inconceivably small, far smaller than the Planck length. The Planck length is a fundamental limit in physics, a scale of about 1.6 times 10 to the negative 35 meters. This isn't just another small number. It represents the frontier beyond which our current understanding of space, time, and gravity completely breaks down. At scales below the Planck length, the classical, smooth picture of spacetime envisioned by Einstein's general relativity is expected to dissolve into a seething, frothing quantum foam. The very concepts of before and after, of here and there, may lose all meaning. It is the domain where a full theory of quantum gravity, like string theory or loop quantum gravity, would be required to describe reality. The trans-Planckian problem is the stark realization that, according to our standard inflationary narrative, the fluctuations that created our entire observable universe spent their infancy in this realm of complete theoretical ignorance. We are using the physics we know, semi-classical gravity, to describe a process that originated in a regime where that physics is almost certainly invalid. It's as if we were trying to understand the intricate details of a mighty oak tree by studying the molecular structure of the acorn, while having no knowledge of botany, genetics, or soil chemistry. We are extrapolating our known laws across a boundary where they were never designed to hold. This creates a deep philosophical crisis for cosmology. How can we have any confidence in the predictions of inflation, the specific spectrum of fluctuations, the statistical properties of the CMB, if the initial conditions for those predictions were set in a domain we cannot describe? The success of inflation in matching the CMB data is spectacular, but this success is built on the assumption that our physics remains valid even when pushed into a regime that fundamentally invalidates it. The problem questions the very validity of our most cherished predictions. Perhaps the actual quantum gravity-driven beginning of inflation imprinted its own unique signature on those fledgling fluctuations, a signature that was then stretched across the sky. Our CMB maps might be showing us a smoothed-over classical picture that has erased the true quantum gravitational fingerprint of the universe's birth. We may be looking at the answer but lacking the dictionary to read it. Theorists have not been idle in the face of this conundrum, and their proposed solutions venture into some of the most speculative and mind-bending territories of modern physics. One line of thinking suggests that new physics at the Planck scale could act as a kind of censor, effectively cutting off the trans-Planckian modes and preventing them from influencing the observable universe. In this view, the universe has a built-in resolution limit, much like a digital camera has a pixel size. Fluctuations smaller than the Planck scale simply cannot be meaningfully described, and their influence is erased or renormalized away, leaving only the fluctuations that started at or above that scale to be stretched by inflation. This would protect our semi-classical calculations, but it simply moves the mystery one step back, as we now have to explain the nature of this cosmic censor. Other, more radical approaches propose that the vacuum of space itself is different at these extreme energies. Perhaps the speed of light or other fundamental constants were not constant during the Planck era. If the speed of light was effectively infinite in the very early universe, for instance, it could change the relationship between energy and scale, potentially avoiding the trans-Planckian issue altogether. Another fascinating idea comes from the holographic principle, which suggests that all the information within a volume of space can be encoded on its boundary. In such a framework, the notion of a local fluctuation with a sub-Planckian wavelength may be meaningless, as the true degrees of freedom reside on the surface. The trans-Planckian problem, in this light, would be an illusion created by our incorrect, three-dimensional way of thinking about the origins of spacetime. Ultimately, the trans-Planckian problem is more than just a technical hiccup. It is a glaring signpost pointing toward the inevitable intersection of cosmology and quantum gravity. It tells us that we cannot truly understand the largest structures in the cosmos, the galaxy clusters, and the cosmic web, without first understanding the very smallest possible scales of existence. The flawless map of the cosmic microwave background, for all its detail, may ultimately be an incomplete translation of a message written in a language we have not yet deciphered, the language of quantum spacetime. This profound puzzle ensures that the quest to understand our origins remains intimately tied to the quest for a final, unified theory of everything. Even as we marvel at the cosmic portrait painted by the cosmic microwave background, a deeper, more fundamental question inevitably arises, one that pushes past the elegant mechanism of inflation itself. We have this stunningly detailed baby picture from when the universe was 380,000 years old. Inflation provides a compelling narrative for what happened in that first, fleeting fraction of a second, stretching a microscopic patch into our entire cosmos. But this simply pushes the mystery one step further back into the shadows. What were the conditions before inflation began? What, in essence, set the entire cosmic story in motion? This is the profound enigma of the initial conditions, a mystery that forces us to confront the ultimate origin of everything, a realm where our confident physics dissolves into complete uncertainty. To grasp the depth of this problem, we need to consider the traditional starting point of the Big Bang theory, the singularity. This is a hypothetical point of infinite density and temperature where the known laws of physics simply break down. General relativity predicts its existence, but it's a clear signal that our theory has reached its limit. An infinite density isn't a physically meaningful concept. It's a mathematical warning sign that we are missing a crucial piece of the puzzle, a theory of quantum gravity that can describe the behavior of space and time themselves under such extreme conditions. So, did the universe truly begin from this singular point, or is the singularity merely a placeholder for our ignorance? Perhaps the Big Bang wasn't an absolute beginning at all, but rather a transition from a prior state of existence, a cosmic phase change that reset the clock without truly starting from nothing. This line of thinking opens the door to breathtakingly alternative origin stories for our universe. One of the most compelling of these alternatives is the concept of a big bounce. In this cyclical model, our universe is not a one-time event. Instead, it undergoes an endless cycle of expansion and contraction. The universe we live in now is the product of a previous cosmic phase that collapsed in a big crunch. But instead of crushing down to a true singularity, the effects of quantum gravity at the highest possible energies created a powerful repulsive force, causing the collapsing universe to bounce back outward, initiating a new period of expansion, our Big Bang. In this view, the initial conditions for our universe weren't random or fine-tuned. They were inherited from the dying breath of a previous cosmos. The smooth, flat geometry we observe wouldn't be a miraculous product of inflation alone, but a natural consequence of the entropy and structure of the previous cycle being effectively wiped clean and reset during the bounce. Our universe, then, is just the latest iteration in an infinite, timeless sequence of cosmic rebirth. Another radical possibility places our universe within a vast and frothing multiverse. Eternal inflation, a popular extension of the standard inflationary theory, suggests that our entire cosmos is just one expanding bubble in an infinite, ever-growing meta-universe. In this chaotic, high-energy landscape, new bubble universes are constantly budding off, each with its own random set of physical laws and constants. In this scenario, the question of initial conditions transforms completely. There is no single beginning for the multiverse. It may be eternal and self-sustaining. The initial conditions for our particular bubble universe were simply a random lottery win, a fortunate roll of the dice that produced the right combination of forces and particles to allow for galaxies, planets, and life. We find ourselves in a universe that can support us not because it was designed to, but because an incomprehensible number of other, barren universes also exist where life is impossible. The multiverse idea doesn't so much solve the initial conditions problem as it reframes it, suggesting that our search for a unique, fundamental reason for our universe's properties may be futile. The tantalizing question, of course, is whether we can ever move these ideas from the realm of pure theoretical speculation into the domain of testable science. Can the ancient light of the CMB possibly hold any clues about events that occurred before inflation itself? The answer is a cautious but electrifying maybe. The most promising leads come not from the temperature map of the CMB, which was heavily processed by inflation, but from its more subtle features, particularly its polarization and a property known as non-Gaussianity. The standard inflationary model predicts that the primordial fluctuations were almost perfectly Gaussian, meaning their distribution follows a specific, random statistical pattern, like the static on an old television screen. If we were to discover significant deviations from this Gaussianity in the CMB-specific, correlated patterns in the hot and cold spots, it could be a direct fossil of the pre-inflationary era. Such a signal could be the imprint of a primordial cosmic string from a previous phase, or the residual echo of a collision with another universe in the multiverse foam, or even a signature of the quantum gravity effects that operated during a big bounce. These non-Gaussian signals would be incredibly faint, buried deep within the noise, but they represent a potential Rosetta Stone for translating the universe's very first moments. Similarly, the specific patterns within the CMB's polarization, especially the elusive primordial B modes, could carry an imprint of the pre-inflationary vacuum. Different theories for the initial state predict subtly different starting configurations for the quantum fields that were then amplified by inflation. These differences could manifest as a specific tilt or a particular pattern in the gravitational wave background that would then be frozen into the polarization of the CMB. Finding such a signal would be like discovering the artistic signature of the cosmos's creator on the corner of the canvas, a tiny but definitive clue about the nature of reality before our universe as we know it even began. The search for these signals is the driving force behind a new generation of CMB experiments, which are pushing the limits of sensitivity to scour the polarized sky for these deepest of all cosmic fossils. Ultimately, the initial conditions problem is the final frontier of cosmology, a humbling reminder of the limits of our knowledge. The cosmic microwave background gives us a magnificent view back to a time long ago, but it also acts as a veil, shielding us from the ultimate origins shrouded in the Planck epoch. Whether our universe sprang from a singularity, bounced from a previous cycle, or nucleated in an eternal multiverse remains one of the greatest unsolved mysteries in all of science. The continued search for the faintest whispers in the ancient light is our best hope for one day lifting that veil and glimpsing the true dawn of existence, whatever form it may have taken. But beyond the grand puzzles of our universe's shape and origin, the cosmic microwave background serves an even more ambitious purpose. It acts as the ultimate experimental backdrop, a pristine screen upon which the faintest shadows of exotic new physics might be cast. For decades, our understanding of the cosmos has been guided by the standard model of particle physics and the lambda cold dark matter model of cosmology. Yet we know these are incomplete pictures. They don't explain dark matter's true nature, the origin of dark energy, or how gravity fits with quantum mechanics. The CMB provides a unique testing ground for the theories that seek to answer these questions, offering a way to probe energy scales so high they will forever be beyond the reach of any particle collider on Earth. We are no longer just cosmologists, we have become cosmic archaeologists, sifting through the faintest patterns in this ancient light for the relics of phenomena that defy our current laws. One of the most sought after of these relics is the cosmic string. Imagine the early universe cooling from a state of immense, unified energy, much like water freezing into ice. As it cooled, the fundamental fields that permeate all of reality underwent dramatic phase transitions. In some theories, these transitions were not perfectly smooth. They could have left behind defects, tangled knots of trapped energy frozen into the fabric of spacetime itself. Cosmic strings are hypothesized to be one such defect, infinitely long, unimaginably thin filaments, thinner than a proton yet with the mass of a mountain range packed into every inch. They are not made of matter, but are pure wrinkles in space-time, gravitational scars from the universe's violent birth. A cosmic string would be so dense that it would warp the space around it, acting as a gravitational lens. If one were to pass between a distant galaxy and our telescopes, it would create a telltale double image, a perfect twin of the same galaxy. But its most dramatic signature would be written in the CMB. As the universe expanded, these primordial strings would have vibrated and oscillated, generating ripples in space-time gravitational waves. More directly, the immense gravitational field of a string would leave a unique, sharp discontinuity in the temperature of the cosmic microwave background. It wouldn't be a blurry, hot or cold spot, but a razor-thin, linear crack in the sky where the temperature on one side of the line is abruptly different from the temperature on the other. It would be a veritable scratch on the cosmic fossil, a clean, geometric feature that stands in stark contrast to the random, inflationary fluctuations that otherwise dominate the map. Finding such a line would be a direct detection of a topological defect, providing incontrovertible evidence for the grand unified theories that predict such phase transitions occurred in the universe's first moments. It would be a window into a symmetry-breaking event that happened when the cosmos was a fraction of a second old, a fossil from an era of physics we can only dream of recreating. The search for cosmic strings exemplifies a broader endeavor, using the CMB to hunt for the imprints of a multiverse. If our universe is indeed just one bubble in a vast, eternal, inflating meta-universe, then it's possible that other bubbles have collided with our own. The energy released in such a cosmic fender bender would have been astronomical, creating a distinct circular imprint on the surface of last scattering. This imprint would manifest as a large, ring-like anomaly in the CMB temperature, much like the cold spot we discussed earlier, but with a very specific and predictable profile. Scientists have developed sophisticated algorithms to scan the entire CMB map, searching for these telltale circular patterns that cannot be explained by standard inflationary fluctuations. While no definitive collision scar has been found, the very fact that we can now rigorously search for such a thing transforms the multiverse from a purely philosophical idea into a framework that makes testable observational predictions. We are, in effect, looking for bruises on our universe, evidence that we are not alone in the greater cosmic foam. The key to unlocking these deepest secrets lies not in the temperature map, but in the CMB's polarization. The hunt for primordial gravitational waves, those swirling B-modes, is the most famous example, but polarization is sensitive to a whole menagerie of exotic effects. For instance, if light from the CMB passed through a cloud of ultra-light action dark matter, a leading candidate for the mysterious substance, the polarization angle of that light could have been subtly rotated. This effect, known as cosmological birefringence, would leave a specific statistical pattern across the sky, a faint but measurable twist imprinted on the ancient light. Similarly, certain models of inflation that involve multiple fields, or models where the fundamental constants of nature vary slightly across space, would leave their own unique fingerprints in the polarization power spectrum. The CMB polarization is like a high-resolution recording of the universe's birth, and we are only now developing the technology to listen for the quietest, most subtle tracks on that recording. Tracks that hint at particles and forces that have so far eluded every other form of detection. This grand endeavor is what drives the next generation of CMB observatories, like the Simons Observatory and the ambitious CMB S4 project. These are not mere incremental improvements, they represent a quantum leap in sensitivity. They will deploy hundreds of thousands of new detectors, creating maps of the CMB's temperature and polarization with a resolution and precision that dwarfs what the Planck satellite achieved. Their goal is to measure the polarization of the CMB to within a fraction of a percent of its total signal, pushing into a regime where the whispers of cosmic strings, the echoes of bubble collisions, and the subtle effects of exotic dark matter should finally become audible. It is a painstaking, monumental effort involving telescopes at the highest and driest deserts and the coldest and most stable environments on Earth. They are our best hope for turning the cosmic microwave background from a map of what we already know into a guidebook for the physics we have yet to discover, a portal to a deeper layer of reality that has been hidden in plain sight since the beginning of time. After centuries of studying the stars and decades of meticulously decoding the cosmic microwave background, we stand at a pivotal threshold. We have mapped the ancient light, catalogued its profound mysteries, and felt the tremors of potential revolutions. But what comes next, the final and perhaps most exciting mystery, is not one written in the CMB itself, but one that lies ahead of us, the future of CMB observations and the ultimate fate of our cosmic models. A new generation of colossal experiments is now being built, technological marvels designed to listen to the universe's whisper with a clarity we have never before possessed. These are not merely incremental upgrades, they represent a quantum leap in our ability to see, an endeavor that will finally separate cosmic mirages from genuine physical truth. Leading this charge are two monumental projects: the Simons Observatory, currently under construction in the high Chilean Andes, and its even more ambitious successor, the CMB-S4 project, which envisions a network of telescopes at the South Pole and in Chile with an order of magnitude more detectors. Imagine these facilities not as simple telescopes, but as the most sensitive cosmic ears ever devised. They will be shielded from interference in the world's driest, coldest deserts, equipped with hundreds of thousands of superconducting detectors that operate at a fraction of a degree above absolute zero. Their goal is to measure the polarization of the CMB with a precision that makes our current best maps from the Planck satellite look like a faint, scratchy recording by comparison. They are being built to answer one overarching, existential question for cosmology: which of the tantalizing anomalies we've explored will vanish into statistical noise with better data, and which will sharpen and solidify into undeniable discoveries that force us to rewrite the textbooks? This is the grand sorting process that will define the next era of physics. Consider the axis of evil and the hemispherical power asymmetry. Are these genuine signs of a lopsided universe, or are they simply the most prominent fluctuations in a single random realization of an otherwise standard cosmos? The immense new datasets from these observatories will generate thousands of simulated universes based on the standard model with such high fidelity that the statistical significance of these alignments will be known with definitive certainty. Either they will fade, revealed as the cosmic equivalent of seeing faces in clouds, or they will stand firm, compelling us to accept that our universe has a fundamental preferred direction. Similarly, the cold spot will be scrutinized with unprecedented resolution. Is it a rare but natural supervoid, or the scar of a multiverse collision? By cross-referencing exquisitely detailed CMB maps with new, deep galaxy surveys, we will be able to either find the missing mass in that void or confirm its profound emptiness, pushing us toward one of the two radically different explanations. The specific scientific goals of these projects are as bold as they are precise. At the very top of the list is the relentless hunt for primordial B-mode polarization, the swirling pattern in the CMB that would be the smoking gun for cosmic inflation. The current generation of experiments has been locked in a battle against galactic dust and the lensing of the CMB itself, a fog that obscures this faint signal. The new observatories are designed to cut through this fog with brute force. They will map the polarized emission from our own galaxy's dust with such detail that it can be subtracted almost perfectly. They will also measure the gravitational lensing of the CMB so precisely that they can effectively delens the maps, removing that secondary blurring to reveal the pristine primordial sky beneath. A detection of these primordial gravitational waves would tell us the energy scale at which inflation occurred, revealing the physics of the universe a trillionth of a second after its birth. Conversely, if even these powerful machines see nothing, it will force a major reevaluation, suggesting that inflation happened at a much lower energy than many of its most elegant theories predict. Beyond inflation, these experiments will act as cosmic scales, providing the most precise measurement yet of the total mass of neutrinos. These ghostly particles, once thought to be massless, are now known to have a tiny but finite mass, and their collective gravity has subtly influenced the growth of the cosmic web. By measuring the CMB's temperature and polarization to an ultimate precision, and by combining it with data on the large-scale structure of the universe, CMB S4 and the Simons Observatory will be able to weigh the neutrino family as a whole. This would be a monumental achievement in particle physics, achieved not in an underground collider, but by observing the imprint of these elusive particles on the largest possible canvas. Furthermore, these observatories will provide the final, definitive word on the fundamental parameters of our universe. The Hubble tension, the slight mismatch in the universe's expansion rate measured locally versus inferred from the CMB, will be confronted with data of such overwhelming precision that the room for doubt will vanish. The measurements of the universe's age, its curvature, and the nature of dark energy will all be pinned down with an accuracy of well below 1%. This ultimate precision is a double-edged sword. It could beautifully confirm the lambda cold dark matter model, solidifying it as a complete and accurate description of the cosmos. Or, more thrillingly, it could reveal a small but significant deviation in one of these parameters, a deviation that our current model cannot accommodate, pointing unequivocally toward new physics. And that is the ultimate mystery the CMB still holds. After all our looking, the greatest enigma may not be any one anomaly, but the simple, profound question of what we have missed entirely. The history of science shows that when we build instruments that see the world in a new way, we often discover phenomena we never even thought to look for. The pristine, ultra-deep maps produced by these next-generation experiments will be scanned for signatures of physics that today exists only as speculative lines on a theorist's chalkboard. Could we find the imprint of cosmic strings, those topological scars from phase transitions in the early universe? Might we detect the subtle statistical signatures of a non-trivial cosmic topology, showing that our universe is finite and wrapped in on itself like a giant donut? The data will be a treasure trove, and it will be mined for decades for clues to questions we are only just learning how to ask. We are like explorers who have been studying a magnificent, ancient tapestry by candlelight. We have traced its major threads, noted its striking patterns, and wondered at its apparent flaws. Now we are about to switch on the floodlights. The next generation of CMB experiments will illuminate every fiber, every color, and every subtle knot in the fabric of the cosmos. Some of the shadows we thought were monsters will disappear, but others will step forward, real and tangible, revealing a universe that is stranger, more complex, and more wonderful than our standard models have dared to suggest. The mystery of the CMB is far from over. In many ways, the most important chapter is just beginning. And so, our journey through the echoes of creation comes to a close for now. We have traveled from the foundational puzzles, the horizon problem demanding connections faster than light, the missing monopoles that should flood the cosmos, and the unnervingly perfect flatness that defies chance. That compelled us to invent the breathtaking concept of cosmic inflation. We then confronted the modern anomalies that challenge this very framework, the spooky alignments of the axis of evil, the colossal and unexplained cold spot, the lopsided power across the heavens, and the profound statistical silence on the largest scales. We've seen how this ancient light speaks to the lithium deficit in the oldest stars, measures the escalating Hubble tension, and even reveals the subtle, extra blurring of gravitational lensing. Each mystery is a thread in a grand, unfinished tapestry, and together they tell a singular, powerful story. The cosmic microwave background is not a settled relic, a dusty fossil in a cosmic museum. It is a vibrant, dynamic, and living field of research. It is a conversation with the universe that is still very much ongoing, a dialogue where every answer we think we have secured only leads to deeper, more fundamental questions. The true wonder of this endeavor is not just in the mysteries themselves, but in what they represent for our species. Here we are, insignificant creatures on a pale blue dot, using the light from the universe's infancy to question the very nature of reality. We are using the afterglow of the Big Bang to probe for cosmic strings, to search for bruises from collisions with other universes, and to question whether dark energy is constant or dynamic, holding the key to a cold heat death or a cataclysmic Big Rip. This ancient whisper, after traveling for over 13 billion years, is now being scrutinized by our telescopes and decoded by our minds, pushing the boundaries of knowledge into realms once reserved for philosophy and myth. The CMB is our ultimate time machine, and the puzzles it contains are the most challenging and exciting crossword the cosmos has ever devised. They are not dead ends, they are signposts pointing toward the next revolution in physics, a revolution that may well involve a new understanding of gravity, the discovery of the dark universe's true identity, or the shocking confirmation that our cosmos is but one bubble in an infinite, frothing multiverse. This story is far from over. The next chapter is being written right now by a new generation of telescopes, the Simons Observatory, CMB-S4, and others, that will look upon this ancient light with eyes sharper than ever before. They will seek the definitive whisper of primordial gravitational waves, weigh the neutrino with cosmic scales, and deliver a final verdict on the anomalies that both haunt and inspire us. They will either solidify our current model of the cosmos, or more thrillingly, they will break it wide open, guiding us toward a new and deeper truth. The greatest discovery might not even be among the 25 mysteries we've discussed today. It could be a completely unforeseen signal hidden in the data, waiting for the right mind, the right algorithm, the right moment to be revealed. This is the exhilarating promise of fundamental science. The universe is always more clever, more strange, and more wonderful than we can possibly imagine. So, as we end this exploration, I want to turn the question back to you. Look up at the night sky with new eyes, knowing that its deepest secrets are written in a light your eyes cannot see. Which of these 25 mysteries captures your imagination the most? Does the philosophical shock of the axis of evil, hinting we might live in a special direction, stir your curiosity? Or does the sheer, apocalyptic possibility of the Big Rip, a fundamental unraveling of all reality, fill you with awe? Perhaps it's the haunting quiet of the large-angle correlations, suggesting a universe with a finite and complex shape that you find most compelling. I invite you to share your thoughts in the comments below. Let's continue this cosmic conversation together. Your curiosity is part of this grand human adventure. Stay wondering, because the next great cosmological revelation is hidden within this ancient light, and it's waiting for someone, perhaps even you, to help